So if you all are settled down, I can begin. Okay, thank you for the nice introduction. So I hope you are enjoying the Muna summer camp here. Today I'm going to talk about group theory and symmetry, and I apologize that I'll not be dealing with details of the mathematics. So if I can request you, please all of you close your notebooks for at least for this 1 hour of lectures. So I don't want to write anything because I want you to get a feeling of developing the notion before I go to the axioms, the postulates of the theory. So you please feel free to close all your notebooks. So I want your attention on the board. So because before, as I said, before going to the axioms, I want you to have the feel of the notions of the subject. So please close your notebooks for first 1 hour. So you drove your car?
Yes.
Oh. So I had a good interaction with Utkrit, and he is very fond of automobiles. He has a good knowledge. So I have a small question. How many times you filled your fuel? Coming from Nareshwan to here, did you fill petrol or your fuel? You filled gas, petrol?
Yes.
How many times?
How many times?
On the way from Nareshwan to here. Any contradiction, please feel free to stop me. Okay. The car engine, laws on which this car engine is based on, does change coming from Nareswan to Nakhonswan. Correct? Okay. Do you understand what I'm writing? I don't expect you to understand. Okay. Same, I don't expect you. This probably you might have a sense. Okay. Now it's your turn to understand this. Okay. Oh yeah, I searched in the Google Translate. So okay. So all mean the same thing. Okay. This is apple in English, in Thai. This is in Portuguese, Masha. This is the language spoken by Pradeep. This is my language, Assamese. We speak different language, and I don't. His language is very complicated, so I skip that. Okay, I mean the same thing, right? But at once, if I have drawn this, everybody would have understood that I am drawing an apple, right? But it is more convenient for you, someone from you, to use this language, right? Someone from Portuguese to use this, someone from India to use this, and this is something called international. Am I correct? Why I'm saying this? This has something to do with representation. All I am changing is the label, the way I'm going to call this object. Object defined by its taste, mass, color, all the properties. I can write this in different languages. So this is the basis of representation theory. In group theory. Okay. In group theory, it all talks about the way you can transform from this language to this language. Ultimately, your physics has to be the same. Okay. Any questions? For example, coordinate system. To be the origin, or I can choose one that is near to the Burin's office. Doesn't matter. So these are changing the labeling. Okay. And this comes under representation theory. But I'm not, if I have time, I'll touch upon this, but just I wanted you to have a feeling of this. Okay. So now, let me take this apple and go into a little more details. So this is the front view. You agree? The front view of the apple. Right? It's the bottom view. Or probably this is the top view of the same apple. So in all this, there is something which is not changing. That is the apple itself. What is changing is the way you are looking at it, your perspective, right? So this is all about saying things, but to do something concretely, you need some mathematical background to explain that there is something which is not changing even if there is a change. Correct? Okay. Okay. Let me give more examples. So this is one view of a house. The another view could be right from the front. Another could be you don't see B at all. All are correct in their own places. Correct. Okay. But In going from here to here, I am changing something. Either I am changing the house itself, or I am changing my position. Okay, so one is called active, one is called passive. It's your convention which one you call active, but generally I think the coordinate transformation is called passive, and if you're changing the vector or the house itself, that is called active, right? So in all of these, I'm changing something and I'm claiming that there is no change. And I want you to mind this. In all of these, there is no change, after a change. Do you agree? There is no change after a change. But this change and this change has different meaning. Right. When I say there is no change, I'm talking about the change of the object here, the house, there the apple, right? And when I'm talking about this change, I'm talking about the transformation. So group theory is the study of this no change after a change. And you'll know why this is so important in physics, even in chemistry, spectroscopy, and all these subjects. All right? Any questions? So I'm going to talk about, then I need to quantify, right? In mathematics, I need to give a proper definition for this change and this change. So this change I'm going to call transformation. And this change I'm going to say either invariance or covariance depending on the situation. Okay. Now let me say why this is bothering us, why this is important. Because you are people from Thailand, I'm from India, someone from America. If you do an experiment in physics, my results should be same as your results. But if I choose a different course, This chalk has a shape like this. What is the axis of symmetry? This one. I can rotate it by any angle. It looks the same. But now, after this transformation, it's broken into two pieces. This transformation is not covered in this group theory. Okay? This is irreversible. It's a part of thermodynamics. So Gurin is an expert. So, okay. So all I am going to talk about is this transformation. There is an axis of symmetry, or there is a plane of symmetry. If you rotate it like this, whatever, there is no change. Okay. Now let me okay. Okay. Imagine someone is at the railway station. Okay. Call it S frame, and there is a train call it as prime frame. Okay. And this velocity is very, very less than the speed of light. Okay. We apply Galilean transformation law. What Galilean transformation law says, that if it is moving with velocity v, then, and it has coordinate prime coordinate, then your x prime is related to x minus vt. Do you agree with this? The Galilean transformation, right? And you take a agree? Any question? Okay. But if you take d2x by dt square prime dx by dt, what is this quantity? What is this quantity? Acceleration, right? The primed acceleration is same as the unprimed one. And what does it imply? It implies this, right? Then your force okay? That means your Newtonian mechanics is invariant under Galilean transformation. I talked about no change after a change. After a change. The change here is the Galilean transformation. And no change means I'm talking about Newton's laws. Newton's laws didn't change after the Galilean transformation. So Newton's laws of motion are invariant with respect to Galilean transformation. All right? Right. That means you cannot distinguish S prime frame if you are performing an experiment inside the train and one who is on the station. You cannot distinguish by any means that these two frames are different, right? Okay. So now again going back to this apple story. It's a popular apple story, right? You know, Apple, it was not the first time that Apple failed before Newton. Apple was falling on the ground from the time immortal, and Apple was falling before Newton from his childhood. But Newton realized that the laws that makes Apple fall on the earth is the same as the law that governs revolution of the moon around the earth, right? So can you figure out that there is a uniformity in the laws of physics? That's why I begin the question by asking, did your engine behave differently? At least the laws of the engine? No. Okay, there will be some breakdown. There are ranges. For example, Newtonian law do not hold good for all over the universe. There are some limitations. There are some ranges for which a theory works. But within that range, there is a uniformity in the laws. Right? Okay. So okay, I know some of the people are interested in cosmology. At least I know about you. Yes, yes. You also? Okay. So I'm sure you have touched upon general theory of relativity, right? All of you. You know something about general theory of relativity. Okay, general theory of relativity is the subject of, it talks about geometry, right? Geometry of space, geometry of space-time, right? And when you send a signal, light signal, how does it behave? When it goes through a massive object, how does it behave? Light bends, around the massive object it bends, right? Because the massive object changes the geometry of the space-time around it. Therefore, light has no option but go through that curved linear path, which is the straight path in that space, right? Called geodesy. So general theory of relativity is based on the mathematical foundation called differential geometry. Differential geometry. Differential geometry. Okay? But differential means talking about an infinitesimal definition of length, say ds square. But the way Pythagoras developed his geometry, the Euclidean geometry, started from some axioms. He had some axioms that worked well on plane, right? And he started building theorems out of that. Okay, that you can, for example, you take a potato. Okay, right? Axioms of Pythagoras Euclidean plane, that you take two straight lines, two parallel lines, they will never meet. Even at infinity, they meet at infinity, that means they never meet, right? There are some set of axioms on which you can build whole lot of theorems that defines your Euclidean plane, the Euclidean geometry that we learned in our school. But if I have a complicated surface, like a surface of a potato, can you figure out the geometry of the surface of the potato right away? Simply, it doesn't hold Euclidean laws, right? Geometry of a surface of a potato. More complicated. If you take the axiomatic approach means you start with some axioms, postulates. Those are given. Axioms means they do not need any proofs. At least for physicists' definition of axioms is no proofs are needed. Those are given. Light travels. If they are parallel now, they will be parallel forever in Euclidean space. There is no way to prove it. This is an axiom. Can you find the axiom of a potato on the surface of a potato? Okay, even if you try for 5 years, 6 years, you may be able to find the axioms that works on the surface of a potato. But for a different potato, the axioms will be different. Right? So it's not possible to have a general set of axioms for the surface of a potato. What you do in that case, you understand how this line element, that is the definition in Euclidean plane is like this, how this line element for an infinitesimal line element looks like on the surface of a potato given any point. That means we are generalizing it to, there are some coefficients here. Right? There will be some coefficients will be sitting here. Okay? Okay. And GR talks about that. General theory of relativity gives you a platform to do physics in any geometry. Right? Those are called, of course, by any means I mean Riemannian geometry, or rather pseudo-Riemannian geometry, which signature minus, plus, plus, plus. Right? Okay. Now let me ask you a small. I started with the axioms of Pythagoras. The two straight lines will meet at infinity. That means they never meet. I ask you the same question for general relativity. Will they meet? Is it same as this? Let me ask you. Will they meet? I don't know. Is there any possibility for them to meet? Maybe, yes. Maybe. May not be. You don't know. We don't know. Right? We don't know. Let me ask you a different question. Is it possible for this ray of light that you have sent tonight with your torch to get back to you in any time, far, if you happen to live for thousands of years? You do not know, but is there a possibility? There is a possibility, right? That means you are allowing the space to bend onto itself in your mind, right? Agreed? All of you agree? You stand here today and take this light. At night you throw it. My question is it a possibility to get this light back onto yourself? You see this, that means saying that you are seeing your own image without a mirror. Is it possible? Mathematically, might be possible, right? But at least GR doesn't talk about it. GR, General Theory of Relativity, that talks about this infinitesimal line element, doesn't talk about let me use this term, the topology. Okay, it doesn't talk about this topology. For example, let me I have this donut for you from last evening. Okay. Suppose our universe, we are sitting here on the surface. I throw a light signal this way. And our universe is not this small, right? After many, many light years, thousands of years, if you happen to live, you will see your own image if your universe is like this. Because you start here, you send a light signal here, it will get back to you, right? But GR talks about local geometry. It's infinitesimal. GR doesn't talk about the boundary of the universe, right? It talks about local geometry. At that local is at the level of cosmology, 10 to the power megaparsecs, you know, that local is not this local, you understand? But it doesn't, GR assumes a topology. There is, to the best of my knowledge, there is no theory that talks about, that has a, see, how GR works. Put some matter, the space-time geometry will be bent, right? Then can you say that for this matter, my topology would be like this or like that? Right. What I'm doing here, you imagine space to be like this. In all directions, right? GR says there may be band depending on masses, right? But you never know if this is repeating. You never know if this is repeating. You never know if this is not repeating also. But in the torus, the mathematical definition of this donut is called torus, which looks like this, right? It is rotating, sorry, it is repeating. It is repeating itself. So there are a group of cosmologists working in this direction. I think you would know better. Ujan, right, from French. Yeah. They're working to find the topology of the universe. Okay. If you take two-dimensional figure, two-dimensional plane, there are definite sets of topology allowed. If you take three-dimensional, I think 18 number of different topologies are allowed. Then, if they are looking for some stars that look exactly alike. See, this is nothing but, if you block it, so this is one universe, but the boundary of this universe is same as the boundary of this universe. Therefore, the stars here is same as the stars there, right? So here doesn't talk about the topology of the universe, right? GR as a theory doesn't talk about the topology of the universe. Okay? By topology, what do I mean is, so okay. Okay, so this is a very bad model, but I asked my wife to build it for you. So this is wet floor. It's eatable. Eatable if you bake it. Okay. So this is a cup. If you consider it, please bear with my model. Is this a cup? If not, at least Japanese cup. Okay. So can I make it a donut? Can I make this a donut? Yes. Can I make this? Yes. Right? Okay. You know how to do this? You cannot cut and paste. You cannot cut and paste. Right? I'm going to destroy the coffee mug, and I am not cutting and pasting. All I am doing is, it's a donut. If I do this continuously, so it is almost a donut now. Right? What I did here is a very complicated topic in group theory called homomorphism. You're continuously changing something without cutting and pasting. There are mathematical definitions of it. For physicists, we understand it is if you are not cutting and pasting and changing the shape, did I change the geometry or not? Going from the coffee mug to donut, did I change the geometry or not? Of course, I changed the geometry. Coffee mug has a different geometry than the donut. The shape and size are changed. The coffee mug has a different geometry than the donut. But there is something which is same even after the transformation. I repeat this. No change and I want you to answer what is that didn't change going from the coffee mug to the donut. What didn't change here? The hole. There was one hole and there is still one hole. Okay? In more technical language, that is called Euler characteristic. Okay? The Euler characteristic is top Euler, E-U-L-E-R. Euler characteristic does not change after a transformation. What is the transformation? Homomorphism. Without cutting and pasting, if you are molding it, the Euler characteristic, in this case the hole, doesn't change. The number of holes doesn't change. Correct? Okay. It's almost 1 hour now. I'm going to wind up my first hour. So before that, I started with Woodcraft's car engine. Then I talked about the Apple, which different language, then with different perspective, rotation of the different, let's say perspective. Then I gave an example of all these houses, right? Looking from a different angles, right? Different sides, right? Then I talked about Newton's laws. Then I talked about Galilean transformation, Newton's laws of gravity. Then I talked about Galilean transformation, right? And at last, I talked about topology. The coffee mug and a donut. I don't know the spelling of donut, so. Right? And all these come with no change this change I name it as transformation. And this change, let me call it invariance or covariance depending on the situation, right? Same topology. One is homomorphically related to the other, right?
You say that the GR is a local curvature, right?
As a theory, it's local, yes.
But and you said that cannot predict the whole.
It does not predict the shape of the universe. Given the fluid, the cosmic fluid, you know the geometry of the universe. For you, it is not local. The definition of local is relative here. For an astrophysics, ZR is global, cosmology is global. But for a topologist, he would say, no, I cannot know the shape of the universe from your Einstein equation. You are taking a partial derivative. Partial derivative is like, you are not taking your boundary, you make everything zero, you forget, right?
But in cosmology, we have predict the shape of the universe, like a sphere, like a flat, like a circle.
Yes, you choose it. You choose it. You do not predict it. You choose k is equal to, I understand what you're saying. You choose k is equal to 0, 1, minus 1. You choose it. You do not predict this. Right? There's a difference. You choose your topology in GR, to the best of my knowledge. I do not know any theory that predicts, given a physical system, that predicts the topology. I do not know any theory. But given the fluid, given the matter distribution, energy matter distribution, you predict the geometry. That's ZR. Correct? Yes.
That's why you say local.
Local.
That's why you say local.
Yes, yes.
Choosing is not predicting.
Sorry?
Because of choosing, not predicting. That's why you said local.
No, local means the scale. The scale on which you are operating. Okay. The global, I mean the ultimate shape of the universe. What is the boundary of the universe looks like? GR has no say on this. It is silent. You choose it. It is infinite. For k is equal to 0, flat inverse, it's infinite. For k is equal to 1, it's going, as you said, it's going to be closed somewhere. You're choosing it. You're not predicting it. Right? Now, I have been emphasizing on this no change after change. I wind up now, my first hour. Please appreciate this, that the hardest thing in mathematics or physics is to get the notion of equality. Although the notion of the sign, this sign was introduced to us on our first grade or second grade. After we learned from 1 to 10 or 100, we know how to count. This sign was introduced to us, right? Yeah. But this is the most difficult sign I have encountered. Let me ask you a small question. If x is equal to 2, y is equal to 2, is x equal to y? And I stop my lecture with this question. Is x is equal to y?
That reminds me of Thiti.
Sorry?
yesterday night we did try to
Okay,
give a really pure definition of the
Equality.
number
okay,
from the empty set.
okay, okay.
So I would love if you listen to his lecture yesterday. I think it's very similar to this question.
Okay, okay. So do you think x is equal to y in this case? Yes, right? Yes. Then you should ask, what is this equality means? You assume the meaning of equality. You assume it. You assume this, the equality means you assume that it's the numerical value it is taking. But there is a definition of proper, I mean not going into that, due to a mathematician says, when you say something is equal in all respect, I and some poles are equal, both are human, right? My left hand and right hand are equal, they can congruent. But my hand and your hand is not going to be equal.
The same right hand.
But it is similar. They are similar. They are similar. X is not equal to y in all respect. I mean, x does not look like y. X is this. Y is this. X is not equal to y in all respect. X is equal to y only in the sense that they have the same numerical value. That's the notion of equality. And there is, even in mathematics, there is no absolute notion of equality. All are relative. What are the properties you are going to consider? Here, the numerical value, right? Even if I write, for some people it will mean the same thing. But if you consider their shape and size, they are not. So same in group theory. It depends on the transformation. When you talk about invariance, you should mind the transformation. When I talk about donut and the coffee mug, I'm changing the geometry and still saying that they are the same object topologically. So the equality here is the homomorphism. The equality in the case of apple would be something, maybe isomorphism. So there is no absolute equal sign. All we have is this.
Or like that.
Or like that. Yes?
Like that.
Oh, this is equivalent. Equivalent. Okay. All we have is either you choose this or this, with respect to the context. Please understand there is a context. When I say that these two are equivalent, donut and the coffee mug, they are not equivalent with respect to the geometry. They are different. Okay? So here I end my first hour of talk. So see you after half an hour. For the second hour. So I hope you understood at least the basic concepts of what I have talked about. Like no change after a change is well understood. I assume that you understood that. Okay. So now we have, I have not expressed anything mathematically yet. But please bear with me that even my mathematics is very poor. So again, I will rely on physical intuition, physical concepts more rather than mathematics. So I'll be more physical in my approach, use less mathematics. But I need to give some theorems. I'll not go into the details proof of the theorem. Just I will understand it by intuition, that the theorem is true by intuition, by our guessing. Okay. So I talked about no chains after the chains. That means I have talked about that when you do a transformation. I'm just starting. So yeah. So when you do a transformation, there is something that is invariant. We have to study the invariance. And if you see, for whole my lecture, I will be relying on those examples. So I talked about this house, right? So I said that, okay, let me again begin by this. So this I call A, right? This I called C, this I call B, right? Now I made a rotation, okay? Let this be the axis, and I made a rotation, or probably this way, okay? This is completely A, right? But the same house. House is not changing. The same house. Okay, same house. I rotate it, I got A, completely front side. Okay, now I ask a question. Can I reverse the process and go back to this? Yes? Right? The reverse rotation. I have a house and I made it this way. I rotate it. Then I can do this, right? Go back to this. That means the transformation T is reversible. Mathematically, we call it inverse of the transformation exists. Inverse. Opposite. If I can come from here to here, I can go from here to here. Mathematically, we call it inverse. All right? Okay? Okay. So inverse is there. The transformation can be inverted. Okay? If I go this direction, I can come back. If I rotate this way, I can invert to get back the same position. Okay. That means if your T is an operator, I can make T inverse, right? Okay, as some folks suggested me to make blocks. Okay. So, okay. Here I write inverse. Okay. So that means this is possible? Yes. Any doubt? This is possible? I put T here. T is an operator. Let's understand it that way. That rotates the house, brings to this position. And here, if I say this is H is my house, I do this, I got this. Then I again do this, then I get back this one. Yes. That's I say inverse exists. For inverse exists for symmetry. All right? Okay. Look at this position. This is the original position. The original, what you started with. T inverse T is equal to H. So that means here it is 1, right? I got a second thing. Identity exists for symmetry. All right? From a simple example, we are getting some conclusive remarks. We are drawing some conclusion about the nature of this operation, nature of this transformation. Okay, you learn that inverse is there, you know that identity is there. And the property of this identity right? Identity is like doing nothing, right? You can say that it's doing nothing. Inverse will do the opposite. If T does something, T of inverse of T will do opposite. Clear? All of you? And identity does nothing. Identity also keeps H invariant, and other operation also keeps H invariant because you are talking about the same house. You are not changing anything. Only the way you are looking, it changed. Correct? Okay. Now, let us make another operation. This is a complicated operation. Let's say now you have gone to the top of the house, or if you can rotate the house like that so that you can see the front house and the this one, what we call it, terrace, right? So this is another operation. So if this is T1, say this is T2, okay? So this house, you are bending it over, right, to see the above portion. Now you can see the C, right? So that is another transformation. I call it T2. All right? I call it T2. But this is the same house. Same house, isn't it? But how did I come here? I take a house, the first one, this is the second one, this is the third one, same house. I'm just labeling it, naming it by different names. I reach the house 3. First, I apply by T1, right? Then I apply by T2. If I do it to house level with 1, I get house level with 3. Correct? Any question? Yes, please.
So the second property, identity, you say that doing nothing. If I rotate, maybe 180 degrees, it comes from the same thing. It is identity or
360, not 180. 180 will flip it. If I do 180, I go this.
not 180, 360.
360. 360, I come back to my original position.
Yes, this is
Yes. That is like doing nothing.
Okay.
Like doing nothing, I'm saying.
Okay.
Okay?
Doing like and doing nothing.
Doing nothing. You get the same image, right? Okay. See, now I was talking about Okay. So I operate first with T1, got this one. Then I operate with T2. Okay, finally to reach house number 3, house 3. Okay, is it the same house?
Yes, it's the same house.
Same house, right? Okay, same object, right? That's a good way to say. Same object. In this case, it's house. That, yes, sorry.
Same object and different image.
Different image, different perspective, or maybe different coordinate system. I cannot rotate the house, but I can rotate myself. Yes. I can go to the top of the house and see, right? That means two different transformation gives me a new transformation. Transformation is new, but the object is still same. There is no change in the object, no change, but this is new. T2 into T1, T2 times T1, it's a new transformation, correct?
Yes.
Okay, so T2 T1, that is, you are making a composition of the transformation. Composition of transformation. And interestingly, this is still a transformation. This is still a symmetry transformation, this product, because the house is still there, only you are changing your angle of looking at it. That means you understood that there is an inverse. For every operation there is an inverse, there is an identity, that means doing nothing. And if you take two symmetry, that is also another symmetry, right? Good. Then what else? See, here I assume that, in all of this I was assuming that there is in mathematics it's called binary operation. You can take two things and define an operation. This could be plus, this could be multiplication, the usual multiplication, this could be matrix multiplication, anything depending on the context. But there exists a binary operation that takes two transformation, two symmetry transformation, and make a new symmetry. Correct? Okay. I repeat, T2 binary transformation or binary operation with T1 is a new transformation, but the house remains same, but this is a new symmetry. By symmetry, when I say symmetry from now, that means something is invariant, that something is the object. Okay, so there is a binary operation. And if you take the collection of all this symmetry operation, they are closed. By closed means you multiply T1, T2, there is a possibility that you will get T3. This will be clear as you go ahead, but by closed means you take this operation, close with respect to this operation. Okay, whenever I say something, that is with respect to this binary operation. Okay. Okay. I am here now. I rotate myself 180 degree, right? After 180 degree, this is one rotation, 180 degree. My right side goes to left side. This is one rotation. I may again make 180 degree. That is, I make T180, T180. Did I not get 360 degree? Right? Okay. but 360 degree is a part of this set. When you cover the full symmetry set, is a part of this set. Do you understand now? T 180 degree. I make one transformation, 180, right? I again make one transformation. What I get? The identity. Where I start from, I get back to the same position. Identity. But that identity is there. I already said, identity exists. So, if you take this symmetry or set of all this transformation, suppose there are n number of transformation for a given object, say house, this house. Okay. So, one of them, I said T inverse exists, must exist. Otherwise, it's not a symmetry. I broke one chalk, you know, for you. Again, I'm breaking it. This is not a symmetry because the inverse does not exist. It is irreversible. Okay. So, one of those will be its inverse. T1 inverse must be one of the elements from here. You agree now? Because you are talking about the symmetry, set of symmetry of the whole set of the symmetry of the house. M, which is like this. And we are not going to make it, you know, T1 will not appear twice. They only appear once. But when I say closed under this binary operation, okay, that means if I take any two transformation, take the binary operation, the result is already there in the set. That's what I mean by closed operation. Closed with respect to this binary operation. And it depends on the context. Sometimes it could be plus, sometimes it could be usual multiplication, sometimes it could be matrix multiplication. Am I clear? Okay. So, okay, I want you to appreciate this. What I did here, I wrote the axioms of group theory. Which is simple, that's why I started with examples, because I'm not a mathematician. I started with examples, and I'm trying to build up the axioms of group theory. And as I said, for Pythagoras geometry, if you know the axioms of the group theory, all theorems can be derived from the axioms. Okay? Just with an example, I build up with common sense, with intuition, I build up the axioms of the group theory. So these are group. You can use it, instead of group, you can use it symmetry. Because you are physicist, there's no problem in doing so. So, I have given you already the axioms of the group theory. Okay. Now let me come up with an, can I rub this?
So,
yes.
So, the number 4 will define the operation.
Yes. So, operation actually, it comes here.
Okay. So
Okay. Yeah, I had, because I'm not doing it very strictly mathematical way. Operation should be assumed a priori. At the very beginning, there exists an operation, assume, then this. When these conditions are hold good, they define a group. So group mathematically is defined as G. Z are the set of elements. Set of elements means Z is a set of T1, T2, Tn is a set of transformation together with a binary operation. So group is written like this, purely in a mathematical terminology. Okay. So
it's a group of G binary operation with that 5 properties.
Inverse must exist. Sorry, I'm missing something here. This is not the. There will be another property coming here. I'm missing it. So I'll come to the precise mathematical definition a little while later. Okay. Okay. Yeah, this is from the physics point of view. Yes. I want one of you to come and solve this for x. Or say the answer. Say the answer for. Twice x is equal to 6. What is x? 3. Thank you. Okay. Now let us understand why it is 3 and how did you get it. Okay. So you were so accustomed, you were so expert in this mathematics that you can right away say that this is 3. But there you ask Thiti, he will take 1 hour to say why it is 3, right?
Yes.
Okay, let me, if not 1 hour, let me take 2 minutes. Okay. When you, okay, so I start here. So I assume there is an inverse, there exists an inverse which is 1 over 2 I exist an inverse. See. Okay? I assume associative property. Associative property means you can break this bracket. This is the binary operation. Binary operation is sitting there everywhere. Okay? In this case, binary operation is multiplication. Right? Can I do this? This is the associative property. Inverse exists. I took associative property. Then I say this is 1 identity. X, here it's 3. What identity does? It does nothing, right? So it is x is equal to 3. What I did, these are real numbers. These are real numbers. And my binary operation is multiplication. That means real number, is it a group? Real number with respect to multiplication. Is it a group? Yes? Yes? How about 0? Does the inverse of 0 exist? I said inverse must exist for all the elements. No. Not over multiplication.
Real number without 0.
Yeah, without 0, yes. If you can, somehow can take out 0, probably yes. but real number which addition, I think it's a group. Because for every positive number, you can find a negative number. The inverse exists. You can do associative law. Identity element is what? 0. Identity element for plus sign is 0 because 0 plus x is x, right? It does nothing. Okay. But you can see from here, implicitly you think that accept 0, okay? Accept 0, you think that there exists an inverse, associative law holds good, then there is an identity element, and that's how you solve it, okay? And I add this property here. This property here, that this is associative. That is T1, T2, T3 is same as T1, T2, T3. Everywhere, even if I don't write, please understand that there is a binary operation sitting there. All right? Okay, I can do. If it has to be grouped, it must follow this way. Okay? It doesn't matter the order of multiplication. But T1, T2 may not be equal to T2, T1. May not be. You can try this with, you can look at any book and they will talk about rotations, right? You rotate it this way, then you rotate it that way. Then you do this way, then you do this way. It will not be same, right?
So is associative is a property of a group or is an extra add-on?
Axiom is a property of the group. Group has to be associative.
But then this doesn't include abelian, right? Abelian is an option.
What? Abelian. Abelian is an option. All groups are not abelian.
Forgot all this.
Yeah, no problem.
The number 6 is needed. You think that's a
Needed. Actually, there are 3 axioms: identity, inverse, associative, and closed. Closed under group multiplication. Closed means if you take 2 operation, 2 transformation, multiply it, the new one is already there. That means it is closed. So mathematicians say whenever you say binary, the closure property is already there. Okay. So now I give a precise mathematical definition now. By precise I mean by the standard of a physicist.
Sorry.
Yes, please.
You say that, can you explain again about the real number is group or not?
Yes.
It's not group, right? Or real number?
You first talk about the transformation, binary operation.
Yes, in the binary equation.
What is that? Plus or multiplication?
Yes, because
Addition or multiplication?
inverse of the 0 is not existing in that real number.
If you are talking about multiplication, inverse of 0 does not exist.
Yeah.
Then it is not a group. But if you talk about addition as a group multiplication, when I say group multiplication, I mean this. This could be either plus or multiplication or matrix multiplication, anything. I need to first define this. When I say real number is not a group under multiplication because inverse of 0 is not contained in the real line. Real line is finite. You cannot define infinity here, right? But so therefore it is not a group under multiplication. But if you change your operation to plus, then it's a group, because for every element there existed inverse on the other side, and identity is 0. You add 0 to it, nothing changes. So this group multiplication is quite a general thing. Please understand that. Do not assume it to be multiplication. When I say group multiplication, that means I'm talking about the binary operation. All right, Mike? Okay? Yes, please.
If you change the change the plus, right, not plus operator, and this inverse of 0 is not 1 over 0.
So take 0. Inverse of identity is what? Identity. Inverse of an identity is identity. Identity is means doing nothing. Inverse of doing nothing is also doing nothing. Right? Okay. All right. Okay? Okay. So you have by now already built your foundation, the axioms. Okay? That means I assume the closure. Okay? I don't know whether my spelling is correct or not. And there is a binary operation. Okay? And the group is defined like this. So Z, and there is a binary operation. Okay. Then existence of inverse, then associative, third is identity. I think that's all. If you assume it's closed, inverse, associative, identity, that defines a group, and it is denoted by G, this group multiplication. And this group multiplication is just a binary operation. It could be plus multiplication or matrix multiplication depending on the context. All right? I have now given you the mathematical axioms. That's all. You can take a note of it. Then I go to some realistic example. So can I move ahead? All right? Okay. So I want you to now answer okay. This is an isosceles triangle. That means this side is equal to this side, but this is not equal to any other. This is an equilateral triangle, means all sides are equal. Square, of course, all sides are equal. This is a hexagon. All sides are equal. This is a circle. So please tell me which is more symmetric. Which is more symmetric? More symmetric.
The most right.
You are saying this one? Any other answer? All of you agree that this is more symmetric? More symmetry means degree. Anyhow you are allowed to do anything. All possible transformations are allowed, and if you need to see that where the degree of symmetry is more. Okay. Okay. So here only two sides are equal. Okay. Now, what is the symmetry? Can anyone say? What is the symmetry of this triangle? Yes, flip it. Yes, flip it. Okay, that means there is an axis. Sorry, my drawing is not perfect, but there is an axis of symmetry. If you flip it, it's same. Here, of course, more than here. Okay, here it's more. Right? Here you can rotate 3 times probably, right? Tuck, tuck, tuck. It will come back to the original one. Here you can do it 4 times. 1, 2, 3, 4. Here 6 times. 1, 2, 3, 4, 5, 6. Here infinite times. Right? So this is more symmetric. All right. Okay, so group theory, what does it do is, we want to find a symmetric group. That means we are interested in finding G star. We want to find a G. Z is a set, you know. It has set of elements. Those elements are transformation elements. Say T1, T2, Tn. One of them is identity. So say T1 is identity, I call it E, then T2, Tn, satisfying all these properties. So mathematically, given an object, finding the group of the object is same as finding the set of transformation that satisfies these axioms. So these are the building blocks. You go for any group, this will be there. Okay? So for this series of lecture, I will prefer taking this. I'll take this as a prototype and try to develop and see what are the additional features we get in this set, in this group. Okay? Okay, let us, have you heard of structure? In mathematics, people say structure quite often. They talk about spaces. Spaces, vector space, Hilbert space, they talk about spaces. Then they talk about structure. They say the theory is, the structure is preserved. Structure. They say the structure is preserved. I should not change the structure, right? So we'll be talking about structure here. Structure means, you know, I said T2, T3 will be a new Tn which is already there, or Tm which is already there. Then can I not make a table? A table. The structure is nothing but for here, it's table. That tells me E, T1, T2, I go up to Tn, E, T1, T2, Tn, right? With respect to this group multiplication, That means doing nothing. That means you will get T1. So, like this, you can build a table, right? We are going to build this table for this, but start with a simple things. This is more complicated. We'll start with some simple things, okay? And this table we call structure of the group. Or the multiplication table. Please understand that. When I say multiplication table, do not confuse it with this multiplication in a real line. This is group multiplication. It could be addition also. Okay, this multiplication means this binary multiplication. Multiplication table or the structure. Once you know this multiplication table, you know everything about the group. Oh, you can write it any order you want. This is the simplest order I follow. But follow one thing. When I write this, the column should come first, then the row. Okay? When this is, for example, this one, first T2, then T1. So this is binary product of T2 first. T2 will act on the object first, then T1. For example, this is rotation and this is reflection. First you do it rotation, then you reflect it. Okay? That's how. That's the convention followed in normally. Okay? So if this is clear that our goal is this. Yes, please.
Is it the convention that you write the H at the end?
H I'm denoting for our house.
Yeah.
The object, yes.
So if you change H or house for our case from the back to the front, is it the convention? I mean, which
that
operation you do first if you change?
when I say H, that means the property of the H, house. T1 will change your perspective from where you are looking. You rotate yourself by 90 degree, 180 degree. All these things will be done by T1. T1, T2, T3. For example, T3 is like 360 or whatever. These are the transformation. Those transformation are acting on this house, the object.
Yes, my question is it the convention to write this way? Can I write
No.
H, T, and E, and you do the operation?
No. This is the convention is that the operator will come on this side. The object will be there on that side because we operate from this side. Okay. First you operate. This is your object. Say H. First you operate with T1. You operate this way. Then you operate with E. Then you operate it up to you. Okay, but all this product must find a place in this table. That's because it's closed, you know, it's closed. So they must find a place in this table. And today, I'm going to, after the lunch, because I don't have much time now, I'm going to find the group multiplication table, the group for this equilateral triangle. Okay, and I'm going to examine the internal structure of this. Okay, so now quickly, suppose I have a group G. It is like E and A. Okay. under group multiplication star. I must follow, as I said, I must follow this. I must follow this. Inverse, identity, associative, and of course closed. Can someone help me in writing the group multiplication table? It could be anything. I do not know. It could be anything. See how powerful this is. This could be anything. Right? It could be, I may be talking about an elephant or horse or symmetry of an elephant, symmetry of a house, anything, a snake, anything. For example, I have only two group elements. One is the identity, identity must be there, and another element. For example, I'm writing it in an abstract way. I want one of you to fill this up for me. So, okay, I fill this up in a simple way. This will be E into E, EA. This is there, okay? I'm not writing. So this will be AE and this will be AA. This is perfectly fine. I want you to answer this one. EA, EA. Applying this concept, I want you to fill up. What will be E into E? Identity into identity. Should be identity. Doing nothing, again doing nothing. Is like doing nothing. Identity. Correct? All of you agree? Okay. What is EA? A? Benji. Agree? Identity. I do a transformation A, then I do nothing. That means A. And here I do nothing, then I do A. That is A. What is this? I will go ahead only if you answer this. And there's a hint. Use one of this property. One of this.
We need inverse.
Huh?
We need inverse.
Yes. I'm asking what is this. Use one of this property.
It should be E. If we need inverse.
According to you, it should be E. Okay. Any other answer? Any other answer?
It's not a group.
Huh?
It's not a group.
It's not a group. But what is the value of this? Okay, one answer from Sampot is E, right? Mike? It's not a group. Okay. Not a group. Okay. Any other answer? Om, any other answer? You can. Not a group. Okay. We have two votes here. One vote here till now.
One vote for E.
Huh?
One vote for E.
One vote for E plus one. Okay.
Define this for group.
Huh?
You said you want to construct group with two elements.
Yeah, I said I want to construct group for 2 elements. The mic is saying that this is not a group. Okay. Okay. Any other answer? Okay. Let's use this. Let's use this. Identity is there already. Is identity there already in this group? That is E. Okay. It already satisfies at least one property of the group. That is the identity. Is inverse there? What is the inverse for every element? What is the inverse for E? E itself. Okay. So at least one is okay. Inverse of E exists in this group, right? Does inverse of A exist?
Yes. Yeah,
It should. It should.
You want to construct a group into a
I want to construct group. I'm forcing this set to be group.
yes.
Okay. So I'm sorry. I have to cut this option. Okay. Then only option is that A is E. So A is the inverse of itself. Then only this is possible.
So A is an identity too, because the only member is an identity that has inverse itself. So both of them are identity of each other.
Okay. So A could be other than identity, but A is such that it is its own inverse. The inverse looks same as the object.
Yeah, so it's identical to the identity. So
No. It will be not identical to identity, because if you do this, it is A, not E. But A is A inverse. Okay. Right? Okay. 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 Now I want you to appreciate this thing. What I did here, see, E and A, right? So E and A, this is a set, right? In this row, let's examine this row. What I am doing? I am multiplying E and A by E. And I said that group is closed. That means if I multiply the group elements by one of the group elements, the group remains the group. It will not give you new elements. Only it will do is reshuffle. It will rearrange your elements. That's what it is doing, see? See? When you multiply with this, you have EA multiply by, in this row what are you doing? Multiply by E. You are getting E and A, right? Because you are multiplying with E. Here what are you doing? A, E, A. What is this? A into A must be E, because this must be closed. You cannot produce something B, because you are given two elements and you are saying that we are saying that it's a group. That means only option is this one. So I'm purely doing it the physics way. This is a theorem. It's called, you know it, rearrangement theorem. Today I'm safe because Thiti is not here. Otherwise, he would ask me to prove it. Okay? So this is a rearrangement theorem. It says that if you multiply your set of group elements with one of the elements, all it will do is rearrange the group. But do you know the set? The definition of set is that it doesn't matter how you place your element, right? So you can write T1 later, T3 first. Who cares? For example, this group has rotation and reflection. If I prefer to write reflection first, then later rotation or otherwise, who cares? Right? But this rearrangement theorem is helping you. Rearrangement means when you multiply, it only gets rearranged, is helping you to know the group structure. Because why I'm emphasizing is because, you know, all this Lie algebra, these quarks, leptons, you know, can be, you know, those quantum numbers can be found from, if you understand this structure well, you can find all these conserved quantities, right? So I think it's already 12. So I will not have time in this second lecture to cover this one. So if you allow me, I can put some theorems there. Okay? So I have already given you the axioms. I have already given you the rearrangement theorem. Or at least I have motivated the use of rearrangement theorem to find the group structure. So let me quickly, this is because, oh sorry. Okay. So let me E, A, B, C. E, A, are you looking at this? No. You are already knowing the answer from there? Okay. Okay. I'm joking. Okay. Okay. Please quickly fill it. This is EA. This will be A. This is trivial, right? So this side, sorry. Oh, sorry. So this is A. I need one more. Yes. E, A, B, C. Okay. E, A, B, C. So A, B. Sorry. E, A, B, C. Here. So easy one, I am filling it up. A, B, C. Now let's talk about this. Please think of it. So let me give this you as an exercise. So E, A, B, E, A, B, E, A, B, E, A, B. Use the rearrangement theorem. What it says that it cannot appear twice. E and A appear only once. A and E appear only once. Rearrangement theorem says it gets rearranged. Okay? We need to apply this only. Okay. A into A. Can it be A? Please answer this. That will be all. Can it be A? No. Who stops us? Rearrangement theorem. Rearrangement theorem says in a column it cannot appear twice. Understand? Do you understand? Rearrangement theorem, after multiplying, what it does? In a row or in a column, either in a row or in a column, it will appear only once. One element will appear only once. So if you are examining row, examine row. Now I am saying examine the column. Do not yes, do not observe this. Okay, your new set is here. A already appeared. What is the option left here? B and E. Okay? If you put E here, see, but B will come here because row also has to have all the elements, but B cannot come here because B is there, right? In the row and in the column, only one time it will appear. So, what will be A into A? B, because B cannot go here. And it must have all the elements. So, A, B, I'm left with E. Right? Now, I already know this one. Now, B into A. And I'm talking about abelian group. By abelian means T1, T2 is equal to T2, T1. Okay. If you know A into B, you know B into A. What is B into A here? If you are using rearrangement theorem, just check this one. A, B already there. It must be E.
So ring arrangement theorem
Yes.
is the theorem that is necessary for a set with operation to be a group.
For to be a group, yes.
It is forced to be a group.
Yes.
So you're using this theorem to force
To
this table to be a group.
to be a group. Yes. Yes. So only option it has is E. Right? B and E already there. Only option is A. Like that, I would like you, this is an exercise. Find this. And maybe you get some two choices here. Two choices. If you are people of 10, I expect 5 of you to have a different structure because two choices are possible here. I'm giving you a hint. Satisfying all the properties of the group and the rearrangement theorem. Remember, rearrangement theorem is coming from these axioms. Okay? So you can directly apply rearrangement theorem to check that this may be having two structures. Okay. So you can take it as an exercise. So in the next class, so it's already 12:05. In the next class, I'll be talking about the group for this equilateral triangle. Okay. So I stop here for now.
So is the A, B related to the pictures you draw?
Which picture?
Are you
These are arbitrary, any group element.
the triangle, right?
Yeah. Okay.
I'm confused that you are trying to put that picture into here.
Oh, okay. No. Okay, that's all for this lecture. So, thank you. So I want your opinion on two things. So whether do you want me to start the new lecture with some theorems or some examples? With some theorems or example? If you're feeling too sleepy, I'll start with an example, or otherwise I can start with some theorems. Doesn't make difference. Okay. Both? Okay. Which one first? Which one first? Doesn't matter? Okay, if it doesn't matter, I should start with theorems.
Yes.
Okay. So you can note down, take a note, and then I will quickly move to the example that I promised, finding the group of the equilateral triangle, right? Is my handwriting okay with you?
Yeah, it's okay.
Okay? My handwriting is okay with you?
I changed my mind.
Okay.
It's beautiful.
Okay, so So it says, okay, not okay. Right and left cancellation law hold good in group theory. Okay. Oh, okay, okay.
Suddenly beautiful, not many people can do it like this. That means we need another double hours, like 2 hours to do it.
Okay. So let Z be a group with binary operation star. Then if AB is equal to AC for some A comma B comma C belongs to Z, then B is equal to C. So it's a direct consequence of axioms of the group theory that the inverse exists, as I said in the morning. It follows from that. So I'm not going to do the proof, so it's because it's straightforward.
Why not for all?
For some is can be extended for all, yes.
For something for all.
Yes. The second theorem says, again, Z is a group which binary represents star. Then the linear equations and x is equal to b or ax is equal to b have unique solution. I think is yesterday in your linear algebra class, Pradeep was talking about existence of unique solutions. Your determinant has to be non-zero. That means inverse must exist, and the axioms of group theory already says that inverse exists. So this has a unique solution. Then I go to theorem 3. Again, she is a group. Then it says, suppose we have two inverse E and E prime as two identity E and E prime. That the theorem says that E and E prime are same and their inverses are also same. Okay? So identity is unique. Only one identity exists. There cannot be two identities. E and E prime, if you find two identities, they are the same. There cannot be two different identities. Okay? So I do not spend more time on theorems. Let me go to the examples that I was talking about. So you can tell me if it is ready to rub. I can rub this? Okay. So in the morning I was discussing about some multiplication table with E, A, then you got this E, A, E, right? Then I asked you to find a multiplication table for E, A, B, C. A, B, C. If any one of you have done it already? Yes? I think you have already done it, right? Can you tell me the entries? Entries here? E, A, B, C. Here? A, B, C. Yes. B? Okay. I trust you. B? C? E. Okay. So A, B, C, E. I do not repeat. Okay. Okay. You need to see here, it should not repeat. Okay? What about this? C, E, E, A. Doesn't repeat. Good. Here? E, A, B. Good. Okay. Okay, a close look into this table will reflect one of the properties of group that may not be always true. Can you figure out this one and this one? It is E here, A here, A here, E here. It's E here, A here, A here, it's B here. Same. It's not same. Okay. Do you find anything like this here? Is there any block like this in this table? I'm asking you to find EAAE, this kind of a block somewhere sitting here. Does it exist? If it doesn't exist, it doesn't exist. No problem. It's not there, right? Yes. Not there. Yes. Okay. E, A, B, C, A, B, C. Okay. Can I write here E? Right? Can I write? Yes. I can, because I have a choice. Yes. As long as I do not violate the rearrangement theorem, I have a choice to put here either A, you have put B. That's also okay. I put A, E. A binary operated with A is E. I assume inverse of A is A itself. That makes me E here. I cannot put B here because B is already here. I must put here C. Then I cannot, only one option, that's B. Correct? Then this one, A, B, C. Do I have any other choice? No. Here, I don't have any choice. But what will be here? B, yes. Here? E. Good. Here? A. E. It's diagonal, not diagonal. Okay. Now do you see? Oh, sorry. This portion. Now do you see disappearing here? Okay? But this is a group of order 4. And this is a group of order 2. There are only 2 elements here, A and E. There are 4 elements here, E, A, B, C. Okay? This smaller group. Now please tell me, if this smaller group, here, not there, there I know. If this smaller set satisfies the axioms of group or not? Can you verify?
Yes.
This, of course. This satisfy, they satisfy there. But this smaller block, smaller set of elements sitting in the bigger set, does it satisfy the axioms of group? That is there inverse for every element? Is there inverse for every element? Yes. A is the inverse of A, and E is of course the inverse of itself. Is there identity element? Yes, E is the identity element. Is it closed? Closed means any combination of E and A should not take you to B or C. It's not taking you to B and C. You are still in E and A. This block at least, this table. So it satisfies all the properties of the group sitting in a bigger group. It obeys the multiplication table of the bigger group, but it itself is a group. When it appears like this, we call it subgroup. All right? So it's a subset of the bigger set, obeying all the multiplication laws of the bigger set, but it's closed. All right? Okay. So my approach has always been to give you an example first, then to talk about the theorem. Now I go to theorem. Yes.
So is it the first to go wrong or?
This is one choice. We have multiple choices here. This is another choice. Okay. So this theorem says a subset H of a group Z is a subgroup if and only if H is closed under the same binary operation on G. This is the first condition. The second condition is the identity E of Z, Z is the bigger group, is there in H. You cannot miss the identity, right? So identity of, that way you cannot say this is a subgroup, right? The identity is missing here. The identity must belong to the smaller set, okay? And what should be the third? Can you guess? I talked about identity, I talked about closure property. The third should be inverse. Yes. For every element of A that belongs to H, the inverse must also belong to H. That's why I said, if you know the axioms of group theory, if you understand the axioms of group theory, you can almost formulate the theorems. Right? So if you're done with writing this,
Is theorem includes the theorem previous? I mean, is the theorem 3 or 4 this theorem?
okay,
Or whatever?
yes, whatever, yeah.
So it's not continued theorem.
It's not?
Continue. I mean, you have theorem 1, theorem 2, theorem 3, and this.
Oh, this, let's call it theorem 4. Doesn't matter. Oh. Okay. So now I am in a position to take up the example that I talked about in the morning. So if you're done with this, I can remove, right? So what we are going to study is the equilateral triangle. Let's say we have this equilateral triangle. Okay. For the sake of clarity, let me label it as 3, 1, 2. Or let me begin with from the very scratch that, okay, I have this triangle, so can you please figure out the symmetries of the triangle? What are all possible symmetry operations that is going to make the triangle invariant? Yes? Rotate. Rotate by how much angle? 3 times. 3 times will make it identical. Right? Okay. So this is a triangle. So we know if we draw a centroid, right? So this sum of all the angles is 180 degree. Correct? So since it is equilateral triangle, all sides are equal. Each angle will be 180 by, correct? Oh, sorry, it's 360, I'm sorry. Okay. So that means each 120, 120, 120. Okay. So if you rotate by 120 degree, let's set it 3, 2, 1. If I rotate by 120, 3 will come to position 2, 2 will go to 1, 1 will go to 3, right? And in that fashion, how many times I can do? 3 times. 3 times will adjust the rotation group, right? Okay. Okay, let me call D rotation by 120. I call operation 120-degree rotation in the clockwise direction to be D. Okay, I call F 240-degree rotation.
120 look like R0.
Sorry.
Look like R0.
Oh, okay, okay. Okay, and I call 360-degree to be the identity element. Okay. You need to choose one convention. If you're choosing counterclockwise, you choose counterclockwise. I'm choosing clockwise. Okay. Is this all? I'm asking a question, is this all? Or do we have more symmetry operations that will make the triangle invariant? You have more? What are those? Flip. Okay. Flipping. Flipping along what? Okay. Along this, right? Along this and along this. Okay. So there are 3 axes or 3 planes along which we can do a reflection, which is equivalent to putting a mirror there, but the triangle remains the same. All right. So for the sake of clarity, let me say this is 3, 2, 1. This axis I call A. This axis I call B, and this axis I call C. They meet at this point. Okay. Now what do I want to build is okay, I think this much space should be enough for me. I want to build the multiplication table, right? So this is my operation. So I have E, A, B, C, D, and F. E, A, B, C, D, F. Yes, let's start filling it. Let's start filling the table. E is E. Same. Okay. Here. Same, because we are multiplying only by E. Sorry. A, B, C, D, F. Okay. Now let's define this operation. A means I flipped 1 and 2, keeping 3 fixed. Okay. So when I take A and my triangle is this, which is 3, 1, 2. After operating by A, I get 1, 2, 3. All right? Okay, now I want A into A. A binary operated with A. So I operate it again with A. Right? What I will get? 2, 1, 3. So this is like E 3, 1, 2. Right? So 2A of the triangle 3, 1, 2 is equivalent to E. Correct? So A is the inverse of A. So it's following the axioms of group theory. The inverse of A exists and that is A itself. So I have here E. Similarly, B is nothing different. B and A have the same nature. So we can guess. If I take B here instead of A, right, I'll be only flipping these two guys. That is 3 will come here, 2 will go there, 1 will remain same. Again if I do the B, that is B square, that will give me E, right? So B will be E, CC will be E. Good? Correct? Okay. So I have a good idea about this. These are what? Reflection. These are reflections. These are rotation. Same here. For reflections, their inverse of it, the group operation is the inverse of itself. Okay? Is it true for rotation? Let's check. I have D here. I take my original triangle, that is 3, 1, 2, 1, 2, 3. D means 120 degree clockwise. 120 degree clockwise will make it 3 will come here. It will push 1 here, 2 there, right? Now let's understand 3, 2, 1. I want to understand, the operation of F on the triangle, on my original configuration. What that will be? F will do 240. 240 is same as 120 degree in the reverse. Do you agree? Okay? So that means this will be 3, 2 will be here, right? No.
I think we have to name quite clearly that it should be anti-clockwise or clockwise.
So this is clockwise.
Yes. So we say
Okay, I have defined F to be 240 degree clockwise. Let me start with that. So 240 degree means, so here and here. So 3 will come here, right? If 3 comes here, 1 will come, 2 will come here, and 1 will be here. Correct? Okay. So now I am to study A into B. So A is sorry, 1, 2, 3. A is 1, 2, 3. I want to study A into B, or say, let's say B into A. 3, 1, 2. So I apply B here. B is, when I apply B to 3, 2, 1, B is this axis, it will flip this one. So I will get 1 will go there, 3 will come here, so it's 2. 1, 2, 3. 1, 2, 3. Okay? Okay? So now you see effect of B and A is same as F. Correct? Effect of B and A on the original triangle. I am applying B and A on the original triangle, which is 3, 1, 2. 3, 1, 2 is same as applying F. Correct? Okay. Now take a closer look. What are B and A? B and A are reflections. Correct? They are reflections. But two reflections are giving you rotation. Okay. So just I want you to note it. B and A means first A will operate. Okay. That means here, right? This is B and A. This is F, right? Okay. In the same pattern, can you please find CA and let me know. C and A going to act on the original triangle, original configuration of the triangle. A will flip this. So 1 will come here, 2 will go there, 3 will remain there. There is an axis C that will flip here. That will make 1 here and 3 here, right? Sorry, 1 here and 2 here, right? No. So first I flip this 1, 2, 2, 2, 1. Then I flip, here was 3. I had to flip here 3, here 1. Okay? So, and what was D? 3, 1, 2. D was 3, 1, 2. Correct? C and A, after flipping, oh, okay, sorry, here is a mistake. So 1 will come here, 2 will come here, then I need to apply by C, and C will make this 2, this 3, correct? Thank you. Is it not same as acting by D? D is doing the same with you. So product of CA is nothing but D. Okay? Do you agree? So CA is D. Now, let us apply rearrangement theorem. A, E, F, D. What is left? B and C. If you know one, you know the other. Correct? So D multiplied with A. Let's do it. D multiplied with A to the original triangle, that is 1, 2, 3. So that will be D 1, 2, 3. D will make a, that is 3 will come here, 2 will come here, 1 will go there. Okay? This is what? See, 2 is still sitting at the original position. Only 1 and 3 are changed. That means it is C. Correct. Yeah. Then what is this? What is left? Huh? B? Okay. Okay. Now I think you can do the remaining stuff. Correct? Okay. Let me write this for you. So I fill this up for you. A, E, it's D here, that is F here, that is B here, that is C here. Okay? So in the B column, I have B, F, E, then D here, C here, then A here. In the C column, I have C, D, F, E, A, B. All right. So in the D column, D row, I have D, DC, A, B, F, and E. Okay? Similarly, in the F column, I have B, C, A, sorry, I have 2B here. This is C, A, E. What should be here? What will be here? D. So please check with the rearrangement theorem that no element should appear twice.
That's column D.
Column D.
F.
Column D. You talk about column D. D, B, C, A, F, E. So A, B, C, D, E, F. Correct? Correct. Please do not consider this. Do not consider this. This is to be multiplied. Consider here, they should not repeat.
D, D, E.
Where?
D, E.
Which one? This one? Okay?
I just okay only one. I approve just one.
Okay. Okay. So if you have played Sudoku games, right? It's almost like that.
I think we could do it like Masroor experiment. We just go again, sit and do
Okay. Okay. So great. So we got the structure of the equilateral triangle. Okay. Do you see like before any subgroup here? No. Do you see any subgroup? You do know do you remember the definition of subgroup already? Yes. Do you see any subgroup here?
Yes. If we consider not flipping, just rotation.
Just rotation. Can you please figure out the subgroup here on this table? Can anyone figure out the subgroup? Subgroup means which must be closed. Which needs to be closed. It doesn't go outside. They have? Can you please figure it out? Yes, perfect. Perfect. Thank you. Thank you. So this is the subgroup. And what is this group? Is it reflection or rotation? Rotation. So rotation is itself a group sitting inside the bigger group. In this case of equilateral triangle. Correct? But your reflection is not forming a subgroup. Why? Because if you multiply two reflection A and B, you go to rotation. You go outside. So that is not a subgroup. And subgroup must contain the identity element which is there. Okay? It must contain the inverse. D multiplied by F is E. So D inverse is F, or F inverse is D. So E, D and F, they form a group inside the bigger group. That's why it is called subgroup here. So rotation group is a subgroup inside the bigger group. And please, I am drawing your attention to this fact that two reflections B and A is giving you a rotation. Two reflection C and B is giving you a rotation. Two reflection A and C giving you rotation. But two rotation D and F is not giving you reflection. That's why this is a subgroup. Yes, please. Thank you. Thank you for pointing this out. This, correct. This is also a subgroup. You take E and A is a subgroup because the inverse of A is A itself. Similarly, is B and E is a subgroup? Is it a subgroup? Yes. If you multiply by B again, it will be E, because flipping it twice will make it like doing nothing. All right? So you can figure out B and E. When multiplied, they become B and E itself. B multiplied to it E. So I take this set. Let me take this set B and E. If I multiply this set, this subset with any element of this subset, say B, what I get? B square and E. Correct? B square and B. But what is B? B is this axis. Here is 1, here is 2, 3. Right? If you do one operation, it will flip 2 here, 3 here. If you make another operation, 2 will come back to its original position, 3 will go back to its original position. So B square is nothing but E. B square is E. So I get B square is E and B. So when I multiply the subset with one of the elements, I get the same set. Only thing that is happening is that they get reshuffled. And your rearrangement theorem says that only the appearance will be reshuffled. Correct? So the closure property is intact. So all this E, B, E, A, E, C, they form a subgroup. Okay? Now let's notice one more property.
You mean all these three together?
Yeah?
One subgroup?
Yes?
You mean all these three set together form a
Oh, yes, that's a good question. Can you put all of them together? Is it a subgroup? No. Why? Why it's not? Why? It will go out because A and B is D, right? So it will not satisfy the axioms of the group. But E, D, F, as pointed out by Chandra, this block is a subgroup.
another central EDF.
EDF, yes,
The other place
yes, ED and F.
in the middle. Yeah, that's also EDF. That is formed by different.
But you are choosing different, B and C.
Oh, right. Hang on. I think actually only, so you have to care about the origin of this or just the operator.
Yes, this can appear many places, this block. But when I study whether this is a subgroup or not, it must satisfy the axioms of the group.
All right, so it's not quotient.
It's not closed. Yes.
Thank you.
Yeah, it's not closed. Yes, I think I need to wind up. One last property. Call it. So cyclic group means, suppose you have E and A, there are two elements, okay? Okay, so A, B, C, there are elements, and all these elements can be formed, say for example B is A square, okay? C is A cube. Similarly, D is A4. For example, I have a group like this. So that means I can construct all the group elements with a single element called A. Okay? In that case, A is my generator. Okay? And the group is cyclic because you need only A. And at some time, a time will come when A to the power n will give you the identity. After that, A n plus 1 will give you A, correct? So can you tell me, is this group, are these groups cyclic? Are these cyclic? Is EA, is it cyclic group? Yes. Can you generate E by A? Yes, because A square is E. Similarly, B square is E, C square is E. Right? Now please answer, if this EDF, which is the rotation group, is it cyclic? Cyclic means there will be an identity element, or there is one element which is the generator, and you can produce all the elements out of that. Is EDF a cyclic group?
I don't follow. Sorry, can you
cyclic group has this property. All the group elements, including the identity element, can be generated out of one single element. For example, A square is giving you B, A cube is giving you C, A to the power n is giving you E. Now my question is, the rotation group here, D, which is 120-degree rotation of the equilateral triangle, F, which is 240, E, which is 360, is this group or subgroup rather, is it cyclic? Can you say that there exists only one group element that generates all? Is it there? What is that? Sorry? I want to write these three elements in terms of only one element. Is it possible for me? Yes? D. Correct. Because 2D, D square, go to the table. D square is giving us F. Because 120-degree rotation will give you 240-degree rotation. Correct? So D square is giving you F. Okay? So there is D, there is D square. How about D cube? D cube is E. So I can write E is D cube. Correct? So I generate all the group elements, all the group elements of the subgroup using one single element, that is D. So D is the generator. Alright? So this is an abstract example I am giving. So here A is the generator, A and A square is the subgroup, where A square is E. Because if you reflect 2 times, you get the identity element. Is correct? I think I stop here. Is there any question? Any question?
This generator is the same in generator in continuous.
No, this I am talking about discrete group.
No, this is the same meaning, right?
Discrete group. I am not touching continuous group. But the meaning is almost same. Any question? Okay, if there is no question, I wind up here, my 3rd lecture. So see you tomorrow morning. And welcome back to the group theory and symmetry lecture number 4. So I hope you were enjoying the campus life here, the lectures, and it's very good that you have seen some practical applications or physical applications rather of group theory in Masroor's class. And today I am going to continue with where I left yesterday, taking a prototype of equilateral triangle, developing the axioms and theorems out of that. So I am going to continue on that. We have produced the structure already, group multiplication table for equilateral triangle yesterday. And on that structure, you have already discovered some properties. The structure has some additional property. So I am going to talk more about that. So let's see. So, but today you have to participate more actively than yesterday. Okay. So I'm using this handwriting because otherwise I get slow. Okay. So, as an exercise again, what this will be? See, this one, A, this one, B, then here, okay. So great. So I've just reproduced whatever we have learned yesterday, and as Donut pointed out, that here is a subgroup, right? It's a group itself, but a smaller set of the larger. And let me use different pencil. Here is a subgroup. Okay? So I list. Let me list the subgroup. Subgroup. EB as well. EC as well. Then EDF, right? Yes. And their inverses are, what is the inverse of C? C itself. Because remember the triangle always. This was A, this was C, this was B. I call it 3, 1, 2, 1, 2, 3. All right. So C is the inverse of B, or C is the inverse of C, B is the inverse of B, A is the inverse of A, and here E is the identity, D is the inverse of D, F is the inverse of D, so D is the inverse of F, right? And D square is D square. What do you expect D square to give you? I'm just revising my D square F. If D square gives you identity, for example, let me take it, D square to give you identity, then D is identity, then D must be inverse of D. But I say D is the inverse of F. Okay, why? I repeat, D makes a rotation 120 degree in the clockwise direction. F makes a rotation in the same direction, total angle is 240 degree. That is same as going in the reverse direction 120 degree F activity, correct? So that's why D and F are inverse of each other, okay? Now I am going to prove a theorem, but as I said, my approach will not be to give you the statement of the theorem, but by doing an exercise. So what I ask you is, okay, let's take this group E and A. This is a subgroup, okay? So I would like you to multiply this group, subgroup, from right. This is your right, okay? From right by one of the element at once, and repeat the process till you get exhausted. For example, I do it once, then each one of you have to come to the board and do it, okay? So EA, this is my subgroup, okay? This is given to me. Number 1, I take EA multiplied by A. What do I get? I get A. I reproduce itself. That has to be by the definition of the group. If you multiply by one of the elements of that group, here the subgroup, you'll get the same thing. Only it is rearranged. That is rearrangement theorem. Right? Great. Now, Samput, could you please come to the board and help me with this? B. Just use the table. No. Okay, thank you. Thank you. Now, can you answer one question? Is this still a subgroup? You can take a seat. It's not a subgroup.
Yes.
Because? Why? Because?
Because B and D is not identity.
D. And yes, identity is not there.
Yes.
Right? So this is not a subgroup. Okay? E and A. C. Benji, please. Please. E, C, look at there. Is this C in type or? Okay. Sorry. So it's C. Thank you. Thank you. So C and A is AC. Please be careful with this. AC. So you need to see this and A. Wait. See how this is. C.
C D
No, 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 no,
อ๋อ
no.
A C F
อันแรกมันเดินมันไม่แถว
แล้วก็
แล้วก็ A C
A A C
So
A C
this is A C
yes F
F,
is not inside.
right? And let me check if Samput has done it correctly. A B D. Okay. Then yes, good. Thank you. Thank you. So I do not agree with your C. Okay. So. Now who is next? Om, could you please come and so A B C D. Okay. So AD is the correct. Correct? What is left? What is left is EA F Chandra.
I'm your friend. I'm your friend. Yes.
AF, so AF is C, correct. So all I am doing is revising your group multiplication the way you multiply. Okay, now one is left. Which one is left? I multiplied with A, B, C, D, F. What is left is E. So the easy one I do it. Okay, EA.
50 multiplied by
That will be A, E, right? I'll just reshuffle. A is E, right?
yes.
And AE is A. So it doesn't matter, I can write EA. Because it's a set, I can reshuffle. Fine? Okay.
Yeah, you use E because
Oh, sorry. I should be E here. So this is already done. Okay. So that I call it, I rename it. Let me call it 1, 2, 3, 4, 5, because there is a reason why I rename, I'll let you know. 6 of them. Okay, this produces the subset. This produces the subset itself, subgroup, but these are not the subgroups.
yes.
Correct?
Yes.
How many elements are here in total? How many group elements are there in total? 6.
Yeah. In group, yes.
6. So this is a group of order 6. Because there are 6 elements. Okay. Now let us forget this. Any question? Okay. Let us forget this. Why? Because it is producing the same thing. I'm not getting anything new out of this. So let's forget this. But when I multiply the subgroup with the elements that is not belonging to this, I always produce a new set, but that is not the subgroup. But I would like all of your attention here. B, D was not present in the original subgroup EA. C, F were not present in the original subgroup AE. D, B were not present. F, C were not present. But multiplying by each element which was outside that subgroup produces all the elements of the group, the bigger group. Please take some time to think of it, because this is important. You took a subgroup. You could have chosen either this subgroup, either this or this subgroup, or this subgroup, or the theorem says if you multiply this subgroup or this one by each element that lies outside this subgroup. If you consider EDF, you have to multiply by A, B, C, like this. Then you produce all the elements of the group, the bigger group. Any question? No question? Yes, please.
So this is like a replacement theorem you said?
No, this is not a rearrangement theorem. This is rearrangement theorem. You multiply, keeping yourself inside the subgroup, take one element of the subgroup, multiply it, you reproduce the same. But this is not a rearrangement theorem. You took it, AE, you are multiplying by elements outside E and A. Do the same with this and this and this. You will produce all the group elements.
When you say order 6, it means what?
All the group elements, B, D, C, F.
6 element of the
Mean there are 6 subgroups?
This is a group of order 6. We took a subgroup E and A and multiply it by one element that lies outside this, and repeat this process with B, C, D and F till we are exhausted. All the elements are outside E and A. Then we produce all the group elements.
But in this case, the number 3 is not a group, right?
This is not a group because identity is not there, not a group, not a.
How the order of the group is actually you count how?
I count the order of group by this. This is 1, 2, 3, 4, 5, 6.
Okay, that's only the way of
Only the way. Yes. I could count this because this is finite. In a continuous group, that's what Masroor was talking about. Angular momentum, you can rotate theta by any angle, right? The wheelchair that you were there, you can rotate theta by any angle. It's continuous. So infinitely many values of theta is possible. I'm not covering that group. That is Lie group, right? Continuous group is Lie group. That was the subject of Masroor. He was talking about all this continuous. He was today doing this, x prime to x plus a. He was doing this, where a is any continuous, any real number. So it is changing continuously. I am not covering this. See, I either go 120, 240, 360. Tuck, tuck, tuck. I do not go continuously because my system doesn't allow that. All right. So I want this to be very clear. But knowing the finite group will help you understand many things. Then you will generalize it to the Lie group. Okay? So that's good. So we got this. We reproduce the group. Now you can check as an exercise that doing the same, which this or this will give you the whole group, will reproduce the whole group. Great? You understood? Okay. Now, let me count one thing. How many elements are there in this subgroup? 2? 2. Okay. And how many distinct sets you got? If you, I say distinct, D-S-T-I-N-C-T. Distinct means not repeated. Yes, thank you. Distinct. How many distinct sets you got by doing this process?
2. BD, DB, CF, FC, yes, 2. 2 distinct. If we include in the EA, 3.
2?
2, yes, 2, yes.
Okay. Yes. So you got only 2 because BD and DB same.
Yes.
CF, FC, they are same. Yes. So you got only 2. Right?
Yes.
Okay. Plus you had the original one. So 2 plus 1. So you had only 3 distinct sets. Those are AE, because you started with AE. If I had started with EC, I would have started with EC. Then BD, since it's distinct, I'm going to cut it. Then CF or FC. So how many? 3? You get 3 distinct sets, not group. This is subgroup or subgroup, but these are not group. You get 3 distinct sets. Any question? Clear? I go ahead. You get 3 distinct sets by multiplying one subgroup. Now I am developing the theorem. You get 3 distinct sets by multiplying one subgroup by right, by an element outside that subgroup. And what is this is the 3 distinct, okay? And what is the order of that subgroup? What is the order of that subgroup? Order, I mean this one. What is the order of the subgroup? 2. What is this? Understand? This is the statement of the theorem. Count the number of distinct subsets that you get by right multiplying. Now I am saying the theorem. Either by right multiplying or by left multiplying. I give it to you as an exercise to see the left multiplying. Yes. Count the number of distinct sets that you obtain together with the subgroup, like EA or EB, whatever you consider. Count those. Those are here 3. Multiply by the order of the group, of the subgroup that you considered, will give you the order of the original. Because, why? Because in totality, you cannot get something more. When you are cutting down the repetitions, what you get is the number of total elements in your original group that we call the order of the group. Because you are cutting down the repetitions. Once you cut down your repetition, sum of all these elements should be equal to the sum of all the elements, I mean all the elements of the original group, right? That's what it means. But it says something important. What it says, if I say this H, okay, right, and this 2 is the order of the smaller group Z, then I call this L. Then my order of the subgroup is always where this L is an integer. Right? L is an integer. You are counting 1, 2, 3, 4. Right? So this is a very powerful statement. If tomorrow somebody tells you that, okay, I have a group of order 6 and I have one subgroup that is of order 4. You can straight away see that, I know, I mean 4 cannot be obtained by, right? An integral divisor of 4 is not an integral divisor of 6. So this is very much a powerful statement. Okay? The order of the subgroup. Okay, now I repeat this. Which EDF? How many elements are here? 3. Into L. I must get 6. So how many distinct sets I will get? 2. Right? Okay. Here how many I got?
2 distinct subsets. 2 distinct sets.
Yes, 2 distinct sets. And by counting the original, it was 3. Right? So here I will get only.
I think that 2 distinct sets.
The order is already 3.
That's order.
Okay, let's do it. Let's do it. If this is not true, if we do not get the same result, the theorem is wrong. Okay, so let's do it. E, D, F. Is this a subgroup? First of all, do you agree? This is a subgroup. The inverse exists here. Right? Now I multiply by A, B, C, right? Now who will do this for me? One of you has to come and do this. Who will come? Donut? Could you please come?
ทำด้วยก็ดีนะฮะจะได้ไม่ต้องตามในอากาศได้เห็นได้ว่ามันเป็นอย่างไรลองจับคู่ให้ดูหน่อยฮะ
Okay, I help you from here. So you have D, A, that is C. Then you have F, A, that is B. Okay. Then?
Maybe share someone to.
Okay, sure.
These 2 guys are very.
Oh, yes, please. My attention.
And let you do this thing.
Yes. So I ask you to write this one, okay? EB is B. So DB, A, FB is C. Yes. Next. Yes. EC. DC. FC. Okay, good. Thank you. Thank you. So anything else? But I do not have any other elements. Huh? Okay, D will give me the same. F will give me the same. E will give me the same because the rearrangement theorem, right? So I will count that to be 1, right? And here, how many distinct sets I got? 1. So that is 2. So distinct is 2, right? What is the order of the subgroup? Oh, sorry, order of the subgroup? 3, 6. We'll always get 6. I mean, not 6, the order of the bigger group. Correct? Okay. Now, let me go to the definition. The definition says these are cosets. We'll not say it's sets. We'll say it's cosets. Okay? When you multiply from right, we call it right coset. When you multiply it from left,
Can you clarify what is the coset of what?
coset with respect to this subgroup. All the distinct cosets with respect to this subgroup. Yes, that is an important point. With respect to what? First, you define a subgroup, or you find a subgroup, then multiply that subgroup by all the elements lying outside that subgroup. Those are called cosets. If you multiply it from right, right cosets. If you multiply it from left, left cosets.
So cosets are the element or is the?
Cosets will produce, cosets are the sets that will produce the bigger group. Okay, and this must follow. Get the distinct number of cosets, multiply it with the order of the subgroup, you get the total number of order of the subgroup, total order of the total bigger group. Okay, that's the statement. Repeat this exercise which I did it for right. You can go home and do the same for left. You'll get the same result. Hope this is clear.
So this is left, right coset.
I did it right. And once you do it right, do it for everyone, do it for right.
So
do not change it.
The coset is the result of this operation.
Yes, distinct sets.
The result.
Each one of them will be called coset. I am counting the distinct cosets that I got. Okay? All right? Okay. Oh, no, no, this together is a coset. After multiplication. After multiplication. This is a subgroup. I multiply with an element outside. If I multiply with an element inside, that will produce the same thing. That is also a coset, but producing the same thing.
In this case, you have 3 cosets.
Yes, 3 distinct cosets. I rubbed it already. Oh, sorry. How many I got? I got two or 3?
3.
I forgot. You please check your notebook.
Yes. You have 3 cosets.
3 cosets. 3 distinct.
Two distinct.
2 distinct cosets. 2 distinct, must be 2, because I have to multiply it by 3 to get 6. 2 distinct cosets. 2 distinct sets. In this terminology, we call them cosets. Or here, to be more precise, right cosets. But the theorem holds for right and left both. Correct? Okay. I'm sure you are very much familiar with this. Pradeep has introduced you, right? No? In the matrix multiplication? No. Okay. Okay, okay, no problem. So we call A and B to be conjugate. If they are related in this fashion. If you can find one element X from the group, okay? You have a group, so G1, G2, G3, Gn. One of them is, say, A, one of them is, say, B, and one of them is, say, X. Okay, and if you can find something of this form, that one element called B is related to A by transformation called, I'm sure this you know, right? Similarity transformation. Then B and A are conjugate pairs. That's the definition.
Just a note, you use this to diagonalize any matrix.
Yes.
So you say they are similar, right?
Similar. They are similar because what it is doing is that this is same as okay. What did I do? This B is a similarity symmetry transformation. I operate by B, then I operate by X, right? So what did I do here? I operate by X, then a new transformation A, then I nullify my original X. I cancel my original X. That is same as B. For example, X is reflection, A is rotation, X is inverse of the reflection. I do a reflection in a mirror, then I do a rotation of the object, then I cancel the original reflection later. I get the rotation.
This is not true in general. This is
Not true, but I say if there exists a relation like this, then we call this is similarity, then this is called B and A are conjugate pairs. Agreed? Okay? So, okay, it's a quick example. We say in quantum mechanics, this is everyone knows, right? Commutating, right? What is this? This is a commutation relation. I'm saying this Hamiltonian that acts on the, okay? Say for example, right? Now I demand Hamiltonian to be invariant under the operation R. Then I can switch R and H, right? I can do that. That means they commute, right? That means if you say this is a new Hamiltonian, right? Then if you say this is a new Hamiltonian, then your original Hamiltonian is related to your new Hamiltonian. This similarity transformation. You are very much familiar with this. So I'm saying things in an abstract way in group theory. Okay?
Is similarity in the same as the commute? A means commute.
Yes, if you say this is Hamiltonian, right? Put Hamiltonian here. Hamiltonian here. Okay?
It's like if you understand in terms of linear algebra, it's just diagonalizing the matrix. If you use X as the matrix of the eigenvectors, then this diagonalizes this. So X is in any other basis. Now you will be the basis of. So you will only have the diagonal entry. After you use the similarity transformation, you can transform your X to produce the same effect but in the diagonal form. So that is all.
It doesn't do like diagonalization.
It's the same diagonalization. Diagonalization you choose X as the eigenvector of the H column of the eigenvector. Then it's diagonalization. It's the same thing.
So now I go to
this is similarity transform you use if you want to diagonalize any matrix. You just have to find X, which is the eigenvector of place eigenvector in the column of a matrix.
So now I go on to say one theorem that if B is conjugate to A and A is conjugate to C, okay, then B is conjugate to C. Conjugate, let me write some. Okay. Do I need to prove it? This is straightforward. It's something like T1 temperature from thermodynamics is equal to T2, T1 is equal to T3. Okay. So then I leave this proof to you. X inverse B X is equal to A, but A and C are conjugate, then there exists another Y. Now we can do substitute and all these things, then finally you will get X and Y, right? Something of this form. I leave this exercise to you, but okay. Then A, I want to prove that B is equal to B conjugate to C. C, B. So only one property will be used, that X Y inverse is Y inverse X inverse. If you use this, you will get this. Okay. So now I go ahead again, go back to the triangle. Okay. Let me take this E B. Oh, sorry, E D F. Okay, and we will see explicitly before. As I said, my approach has been to see from the example, then I make the theorem. Let's see explicitly finding okay, is there an element X that relates D and F by a similarity transformation? That's the question. That x must be, okay, I relax it. X could be anything. X could be A, B, C, D, E, F, anything. Can you find one x that relates D and F in the fashion in this fashion? What is that x? Can you try? Who is willing to come to the board? Mike? Okay, we try together. Please come. We'll try together. But we'll check with each element. That's the way. Now, it took long time. Okay, we start with A. Okay, A inverse D.
Every component.
A. Okay.
Okay.
Okay. Now I make things easy for you. This is 3. This is 1. This is 2. I need this A, right? So I did this. So we do it. Let's do it.
We do in this one.
Now first this one.
Yes.
A will reflect this.
Yes.
You write the triangle here. Yes. 1, 2, 3 remain. Now A inverse D. Yes, right. A inverse D. It is remaining. You need still there. No. I'm saying you operate this with this. A is gone. Now you are left to it.
Oh, okay.
I'm doing this associative property. Now you are left to it. A inverse D. This. Okay. Now D is 120-degree rotation in the clockwise direction.
Okay.
You rotate. Now.
Rotate in the
Clockwise direction. Yes.
one, right?
Yes. A inverse. No. You first
okay.
keep this A. K inverse. You have not used this yet. You have used this A. This is gone. Now you use this.
Oh,
Yeah.
okay.
Yes.
Word again. Word. A. What is A? Okay, this one.
A inverse is same as A. You know. So doing the same thing. Flipping the below index.
Yes. We need to move one.
Yes. What is this? I think maybe we can look at the sample.
Oh yes. I should have called you. Yeah. So is it correct? Is it correct? Chandra, is it correct? Yes, you want to use a table. Yes, please. Correct? Correct? Then, now, what was my original? Original was 3, 1, 2. What was that original that give you this one? Yes. Is it F? F? Okay. I asked you a question here. So X is A. Correct? And you were lucky to try first with A. Okay? Now, let me repeat this with who can come? Ranju? Yes. Yes. Who is interested?
Yeah, for the
Okay.
that's right.
Can you? Would you like to come? Any one of you? No?
เกษตรสู้ๆหน่อยหมุนสามเหลี่ยม
Because I have been not symmetrical. My attention is always on this side, so let me be symmetrical. Yeah. Thank you. Thank you. Yeah. So, okay, let's try B inverse D B. I draw the triangle for you. Yes.
Okay.
Yes. Thank you. Yes. Yes. Okay. B inverse D. Then. Okay. For them, I'm doing it.
Okay.
Okay. Great. Now D, 120 degree.
A, B, C, D. Okay.
120 degree in the clockwise direction.
Okay.
Clockwise. Yes. Let me into a bracket so that they can understand.
Okay.
And B is this axis, so you need to flip it. B inverse is same as B. No, just flip it. 1, 3, 3, 1.
B.
Yes. 2 will be there, no change in 2. Yeah. So
B inward các bạn.
that is 1, 3.
B inward.
Yes. 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 So go, okay. I think it's done.
I need to find it.
Yes. Yeah. Okay. So now I write the original. That is 1, 2, 3. So what will be here so that we get this?
F các bạn.
D inverse.
But D inverse is, you can take a look at D inverse
Yeah.
is F.
Yeah. D inward.
Is F. So thank you. Thank you very much. Thank you. Right? Okay. So I tried with A, I tried with B. Who wants to try with C? Quickly. Who wants to try with C? Yes, please. Benji. You said yes. So I write my results. Wait. I want you to find C inverse D C. What is this? So I draw the triangle for you. This is 3, 2, 1, and the axis C is this. Okay? So you need to find this. So what I got is A inverse. No, you can continue. A inverse D. 1 second. Good. Good. Yes. Now this one. Okay.
C is reflection.
Yes. Okay. So 2 will not come here. See, C is a reflection on this.
Yes.
This is the plane of reflection. This is the mirror. If this is the mirror, what will happen? 2 will go this side. 3 will come back to this position. There is a mirror here. If there is a mirror here, 1 will not go anywhere.
Okay.
Okay?
Then 2.
No. Yes.
2.
What was there here? 1, 2, 3.
Yes.
So 2 will not go anywhere. This is the mirror.
And
The mirror image of, you see, you need to make a reflection here.
T.
Yes, 3 will come here.
Yes. 1.
1 will go there.
Yes.
right?
And 2.
2. Okay?
Yes.
Okay. Now you multiply with D. You write C inverse. Yes. C inverse.
Yes.
Now D. What D does? Rotate by 120 degree in the clockwise direction. Yes.
N.
So 2 will go. Yes.
Yes.
Yes. And
And
C is always this axis. Okay, mirror is here. Yeah.
1, 3, 2.
Nothing will change here. This is on the mirror, nothing changes. This is the mirror. This is the mirror. On the mirror, nothing changes.
Oh. T.
1.
1.
Yes. 2. Good. Okay. Now, this may be little tricky, but you can try. Wait. This is my 1, this is my 2, this is my 3. What is the transformation here that gives you this one?
Sorry, excuse me. We have the break on the 11:30 for the half an hour, and we will continue
Okay.
at the
I'll stop this here. So,
A, teacher.
Hmm?
A.
A.
Yes.
เอากลับไปเป็น1 2 3 1 2 3คือรูปเดิมเลยบรรทัดแรกอะ
D.
บรรทัดแรกของหนูอ่ะ
ไม่ใช่แรกนะ
และรูปเดิมคือ
3 2 1.
จะทำอะไรให้เหมือนเดิม
See, look, take a look at this. This is the original. 1, 2, 3. Or let me say, can you stay here so that everyone can say? Yeah. This is the original. 1, 2, 3. What happens here? 1 goes up. 1 goes up. Okay? 1 goes up. Okay? 2 goes down. Oh, sorry. 2 goes here. 3 goes here. Right? So that is F. F, right?
Yes, yes.
Because F is 240 degree in the clockwise direction. That means 120 degree in the anti-clockwise direction. So finally you have seen that even C inverse D C is F. Okay? Now I don't have enough time. I go on to state the theorem. Thank you. I state the theorem. A, B, C. If I say E inverse D, E is D. What I'm left with? A, B, C, E, F inverse D, F. F inverse is same as D, so that will give me F. Check with here in the middle I put only D. In the middle you put F. Repeat the process. 1, 2, 3. You will always get this subset. This is the theorem. And if, I'm not saying you will always get this, if you get always like this, no matter multiplying, no matter doing whatever similarity transformation you do by picking one or other element from this set or the other set, from this subgroup or the bigger group. If you get on the right hand side elements only belonging to the original subset, this subset is a subgroup, then that subgroup is an invariant subgroup. And why I am spending my time and energy here? Because it's used in quantum mechanics.
So if
Yes, please.
so if the similarity transformation can generate the only
Yes.
member of the subgroup,
Yes.
so that is invariant subgroup.
Yes, you take you have a subset, subgroup, no matter whatever x inverse and x you take, you have elements here.
Yes.
You reproduce one or other element of this subgroup itself. Then that subgroup is called invariant subgroup. And probably, I leave it to you to study. This is the complete set of commutating observables, all these things. I'm not going to, I have no time to go into that, but I give a lead or link for your future. Okay?
Yes.
So I end here.
With we have 20-minute break.
20 minutes break.
We will
Okay.
start at noon.
12 o'clock.
Yes.
Okay.
เลื่อนนะครับเพราะเราเลื่อนลงมาชั่วโมงนึงเราก็จะได้เข้าเที่ยงตอนบ่ายเนี่ย
เครื่องมาทำไมโม
ใช่
เพราะว่าอย่างนั้นเหรอ
ก็อาจารย์เลื่อนลงมา
เดี๋ยวผมเอาเลย
ที่โบเขาบอกไปแล้ว
บอกว่าตอนบ่ายโมงก่อน
ใช่
I think we should have this 1.5 hour break so that you want to continue after half an hour?
Yes, I think. Because this is in, I want to follow up this and quickly finish. My next hour will be small. So,
Okay, so let's have half an hour then. So that
okay, sure. So, this is the final lecture on group theory and symmetry. So, we started out, I just, let me recap, okay, from the beginning. On the day one, on the morning, yesterday, I started out with a question asking to Utrecht about if his engine, laws of his car engine is same while he was coming back. Then I went on to describe about transformation, changes, invariance, covariance, all the stuff by giving more and more examples rather than theorems. Then in the second lecture, probably I introduced the axioms of the group theory. Those axioms are identity, existence of a, there is a set. First of all, there is a set, call it G, and there is a binary operation, and there are a few axioms. One is identity, and binary operation, as you said, is closed. Then identity, inverse, associative. Okay. On the top of that, the group may be abelian or may not be abelian. You have a choice. Okay. Not all group in this nature are abelian. The one that is Abhinav is teaching you, electrodynamics. I think he would stop at electrostatics but electrodynamics is E1 symmetry. E1 symmetry, but that is abelian. But in nature, you will encounter non-abelian groups also. Okay. with these three axioms and with the binary operation, we developed some theorems. Actually, we extracted some results out of this. Okay, and today and thereafter, I talked about the structure of the group. Structure is nothing but the multiplication table among the elements of the group. Okay, how the group elements are multiplying and what are their results after multiplication. They must follow the axioms of the group, and that the multiplication table is called the structure of the group. Okay, in mathematics, structure would mean many things, but at least in this case of group theory, we mean the multiplication table of the finite group is called the structure. With structure in mathematicians say, we come across spaces. Spaces means consistent with this structure, you can have different elements that defines the same structure. Okay, there could be many ways of, I have to use this word, I do not know any synonym of this word. If you know, please help me. There could be many ways of representation of this structure, and that gives rise to representation theory. And one popular representation is matrix representation. Okay, so if you have noticed, I said A, B, C, D, E, F, all these things. What is A? I had to every time explain you that A is a reflection, and you need to see the figure. Every time I need to say, okay, B is this, C is this, but these are abstract, A, B, C, D. This table, if I ask you to forget this triangle, you are given this. You are only given this table, multiplication table. That means you are given the complete information regarding the group. Once you are given the table, the structure, while you learn more about group theory, a day will come you will forget about the triangle. The triangle here is the geometric representation of this table. Okay, let me write, because I should not have removed this. So there is group, there are axioms, right? Identity, inverse, associative, right? Then we get some theorems out of this, right? Now I am saying that there is structure. I already talked about structure, right? And corresponding to this structure, there are ways to represent this structure. The triangle that I have been drawing for last one day at least is the geometrical representation. I am drawing it. I am drawing a geometry. Okay, I could have completely abstract representation of this. I could have coordinate representation of this, and I could represent that in terms of matrices. And in that I will not write A as B, B as like this. Then I will say A, I am sitting on, the triangle is sitting on which dimension? 2. Triangle is on the plane. So I need 2 coordinate axes. Okay, so my matrice is A, so then these all will be matrices doing some transformation of the plane. You learned this from Pradeep's class. There will be 2 cross 2 matrices. Can you quickly say what is that? If you say this is my triangle, and this is your a axis, right? Can I coordinate this as 0, 0? Can I consider x axis, y axis, right? If I take this as 0, 0, then this will be 1, 0, okay? This point, what I call initially 1 and initially 2 and 3, so 2 will be minus 1, 0, yes? Right? And the reflection does not reflect the mirror itself. If you stay even slightly away from the mirror, you get an image there, but the mirror itself doesn't have an image. So this line, this y axis is invariant under this reflection, correct? So can you figure out the entries here? X will go to minus x, correct?
Yes.
Y will go to same. So y will go to y. So here will come plus 1, right? X will go to minus 1, right? This line is not going to mix anything. It's not going to mix x and y. So 0. This is called matrix representation. Is it clear now? Okay. Okay. Now, am I forced to use only this coordinate system? Am I forced to? Do I always have to choose this coordinate system? Am I bound to? I'm asking a question. Am I bound to choose only this coordinate system? No. Transformation is different. I'm fixing the transformation, that is a reflection along this axis, right? Transformation is fixed. I'm talking about the coordinate system. Am I bound to choose this coordinate system? No, I'm not forced. This is my convention because I found this easy. Somebody, one of you, could choose another coordinate system for whom this is x, this is y. Okay or not? Yes? Okay? Then will that matrix be still same? Then there will be a transformation law of these matrices, one which is represented in the original system and one which is after the transformation. This transformation is not A, B, C, the elements of the group. I can rotate the coordinate system by any angle I want. Okay? And that transformation, if that transformation I call T, so T inverse, this is A, my original, to T will give me new A, let me call it A prime. Okay? And what is this T for me? It's a rotation in a plane. I forgot. You need to tell me. Cos theta, sin theta, minus sin theta, cos theta, I forgot. So I forgot the sign. So you can check it in the Google, right? I also forgot. So anyway, the rotation matrix in the plane. Take the inverse of that, and you know all the representations for A, for the original. So you will not be surprised if somebody gives you a different A, different matrix with different values of entries, you will not be surprised. But accordingly, with the same T, you have to transform all of them to be consistent with the group multiplication structure. You cannot do anything with this group multiplication structure. This is fixed. If you transform A in this fashion, you have to transform B, C, D, E, F, everyone. Otherwise, you are going to interfere with the group structure. That is not allowed. All right? And from now onwards, whole matrix algebra would follow. Okay? Because you have represented it in terms of matrices. All right? I'm not going to, because I cannot complete it. So therefore, I'm just giving you the flavor of it. This is all I have been talking for last 4 hours is the geometric representation. Now this is the matrix representation. Got it? Okay. I started with a geometric representation because it was easy for me to convince you. Then I introduced the group structure. Then now I am saying that always I need to, in physics, in theoretical physics, you need to do more algebra.
Okay.
The calculation needs more algebra. Yeah.
Can the transformation matrix member be a member of this group?
Very good question. Yes, that could be. That could be. That could be. Because if this is a rotation matrix, one could be D, one could be F. Nobody stops us. Yes? Okay. I started out with some geometrical figure because that was easy for me to get to the group structure, multiplication table. Now I am saying I am going ahead and going to the matrix representation. I am saying that for theoretical physicists, probably this is more important. The way theoretical physicists are working nowadays I am saying. For them, the algebraic part is more important. Okay? Now I am saying that neither the matrices, probably nor the geometrical interpretation, geometrical representation, but this is the most important thing, the multiplication table or the structure. What is this? More sophisticatedly, this is called the algebra. The structure is the algebra of the group. Okay? Okay. Now, mathematician will give a structure, a pure mathematician will deal with whether that has a geometrical representation or not. Suppose I change many things here. So I make this D, I make this here, and this I bring to here, then you get a new table. It may not be easy to get a geometrical representation because geometrical representation will need your intuition, imagination. Because this was simple, you could do that. So there are people who talks about geometrical representation of the group. There are people who talks about matrices representation of the group. In physics, mostly we deal with the matrix representation, which I cannot cover in this short lecture series, but I'm trying to give you a flavor. Okay? So for the sake of completeness, I will write down all the matrices for this simple equilateral triangle. I'll write down. Okay? And all these matrices you can do a matrix multiplication now to check if they satisfy this or not. They will satisfy. And you can choose a coordinate transformation, what is it called? Rotation in the two plane to find the new A prime, the set of the prime table, and check if they are consistent or not. Okay? So that's all about matrices, matrix representation of group. Okay? If I have time, I will give some theorems, but I want to complete this part. Okay. I talked about invariant subgroup. And I proved that EDF is an invariant subgroup, meaning X inverse, take with any element, will give you this. By set, I mean it can be reshuffled, allowed to reshuffle, allowed to rearrange, but it will give you this. Correct? Okay. Now I am asking you a question. Is this a subgroup? Is this a subgroup? Should be. Yes? Yes. One answer, yes. Any other answer? Yes. How many yes and how many no? Yes. Yes. Yes? Yes? On the right hand side? Yes? Okay. Because its inverse is E itself, and this is the identity element is already there. So this is a subgroup. Now I want another answer, that is E is an invariant is E an invariant subgroup or not? Invariant means if you do this similarity transformation with any element from the here, that should give the same set, same subset. So for example, X inverse E, X should give us E. Will it give me E? It will give me E, right? Because, right? This is E. So E is always an invariant subset, not only of this group. E is always an invariant subgroup. Not only of this group. Because to prove that, I am taking one X that is not A, B, C, D, I am not choosing anything, right? This is always true. Okay.
Will it be true for, say, if I choose in this group, if I choose D?
D.
So D is not inverse of D, D inverse is not equal to.
Okay. Pradeep is asking D.
No, no, D inverse E D.
Okay, D inverse and
No, no, no. D inverse E D. Suppose I choose that. Suppose I choose this X as D.
D inverse E D. It is D inverse E is D inverse D is equal to E.
But D inverse is equal to it. So it will be.
Yes. So D inverse D is E. Okay.
Means if that is true only if the inverse commute with the D, right? Whether it will be true always.
Oh.
No.
This
What I mean to say is
D inverse E or any inverse when you
no, not about this. About that. After you apply E on the D inverse D.
I am not doing any commutation here.
No. D inverse D. I'm saying telling about D inverse D.
It's always E.
It's always E.
Yes. That's the property of inverse.
axiom.
Yeah. Not only D inverse, any inverse when you binary product with that element is E. Okay. So now I go ahead.
And it's only possible if inverse exists. That is the
Yes. But in the group,
inverse always exists.
yes.
Because in linear algebra, it will be a time when inverse may not exist.
May not exist.
So that will not be a group. If
That
the
is not a group.
element is in some set, that is not a group.
That is not a group.
So it's like because in that case, if I remember, so the mapping between two space, if you reduce and increase the space, like 2-dimensional to 3-dimensional, 3-dimensional to 2-dimension, you may not represent it as a group, right? Those transformations.
For group, those three axioms must be there.
No, like for example, when I go from like when the inverse don't exist means I'm going from a 3-dimensional space to a 2-dimensional space.
Okay. Okay.
Something like that, because I am mapping some vectors to the null space.
Okay.
Okay. So that I cannot remap it to the original space.
Yes.
If I extend something, I mean like the projection operator.
That's what is meant by inverse. Inverse doesn't exist means that you cannot have the inverse map. So yes,
All these kind of transformations we cannot represent it as a group, right?
you cannot. For group, I'm repeating existence of inverse, identity, and associativity, and it should be closed. Okay.
So if I say the elements of a vector space is by itself is not a group.
As I said, you need to satisfy these three axioms. If it is not, it's not a group. Okay. So I now conclude. I'm almost about to conclude. So talking strictly about this equilateral triangle, I have E as an invariant subgroup. This is called trivial subgroup also. Then I have E, D, F is an invariant subgroup. Okay. For invariant subgroup, let me state this as a theorem that if you take this invariant subgroup and find the cosets, this is right or left? Right cosets. Right cosets. And if you take the left coset, left coset, they will be the same. Do you believe this or not? I do not have enough time to show this explicitly. Do you believe this from your intuition? Because this is invariant. By invariant means X inverse right? I can write this. When I say invariance of some, say, Z, this holds, right? This holds? Okay? Now this Z, you consider this to be this. Either take one element each time or consider this. Okay? If this is true, okay, then to nullify this, I multiply here x and I multiply here x inverse x e, okay, that what remains? Z x is equal to x z. What is z for me? For me z is e d f x, that is right coset. Right coset, and this is left coset. Okay. Now the theorem says for the invariant subgroup, right coset is same as left coset. Okay. Any problem? Any question? What I'm saying is true? Okay. Okay. So what is this exactly? If you take a close look here, okay, if you see this,
Right is here, left is here.
huh? Right, this is from right. I'm operating from right. This is, I'm operating from left. So, yes. Okay, now I asked you to take a close look at this expression, only at this expression, and nothing else. Take a close look at this expression. Z is fixed, E, D, F. X could be anything, A, B, C, anything. Whatever X I take, A, B, or C, I can flip it. I can flip it. I can commute it. When that is possible? So Z must have some property in this whole group, okay, E, A, B, C, D, F, 1, 2, 3, 4, 5, 6. Which element has this property? Just now Pradeep was discussing it while I was here. Which can commute but keeping the multiplication value same? Which has this property? If, for example, what I mean is AB is not equal to BA, CD is not equal to DC, but which is commutating? Take one example in this, yes, E, A is equal to A, E, correct? This is true only for E. I mean E with anyone.
Yes.
But if you do not consider E with all the others, it's not going to be true. Correct? With E, it seems to be commutating because it's identity. It's like doing nothing. You do nothing before or after, doesn't matter. Okay. So now coming back to this equation. Is it not like, is Z here not acting like E? Do you find some similarity between this Z and E, at least in the sense that this kind of things are happening? Do you see this or not? Here, where Z is, I'm not saying Z is equal to E, I'm not saying that. I'm saying with respect to this property, only with respect to this property, Z is behaving like E. What is Z? This set. What is this? Invariant subgroup. The invariant subgroup is somehow acting like an identity operator.
Just one question.
Yes.
So the group as a whole can act as an entity, but not each element. That is true, right?
Not each element. Not each element. Z is a set. Z is the set. Set. Let me. Because that's the punchline. Yes. Individually, I'm not saying it. When I say I define Z as the set, and I'm multiplying it with X. When multiplying with X, of course, X D will not be D, but it will be F or E. But in the set, I'm allowed to reshuffle. In the subgroup, I am allowed to reshuffle by my rearrangement theorem. So when I consider Z, I consider the subset, as you rightly said. When I consider the subset, set I'm saying, not the element, then Z acts like a identity operator. Then I ask you a question. If I consider Z by me, I mean the set, the subset, the invariant subgroup. If I consider this invariant subgroup as the identity element, can I say that this invariant subgroup is a part of, is an identity element of an abstract group? And that abstract group, I call it factor group. I at least by now proved one property, that this invariant subgroup is an identity operator. So the identity exists. The remaining two axioms I need to prove. For this abstract subgroup, as he asked, this abstract subgroup is not the group elements of those, but are some sets. Because I start with a set as my identity operator. Now I'm going to an abstract level and asking that at least you see one property is satisfied. And if the remaining two axioms are satisfied, I'm going to call that as a group, new group, I'm going to name it as factor group. Can I do that? If I do that, with that, I will wind up. Okay? Now let's see. Yeah.
So since all the invariant subgroup have these properties, is it necessary to give a new name as factor group?
Yes, because it's something extra, because now this whole set is an identity element. Whole set is an identity element at some abstract level. If you generalized your concept of group from here, but keeping those axioms fixed, now I have one identity element. Now I need to check whether other two axioms are satisfied, so that abstract group, which I call it factor group, is just a group on some abstract level. If me, you, and these two fellow, sorry, I don't know your name. Your name, please?
Okay.
Your name?
B.
Your name? Kate. Mim, Kate, Burin, and me form a group. Fine? We have this structure, multiplication table. Now I say Burin and me form a club. These two, Mim and Kate, they have formed a club. I am saying Burin and me together is the identity element. We form the sub-invariant because you multiply us with Mim from the left or right, doesn't matter, we remain the same. We may shift our position. Burin will come to this position, I will go to this position in the set, but we will remain the set. The definition of set is what? You can reshuffle it. So we act as an identity element in some abstract group probably, if we satisfy the remaining two axioms. That is the inverse, if our inverse exists, if Mim and Kate, sorry, Bim and Kate, if they together an element now, if their inverse exists and together as a collection we are closed under multiplication, then we form a group, and that group we call factor group. Yes, please.
So factor group is like a group of groups.
Group of groups, but I cannot say simply group of group.
But
It's a group formed by the sub-invariant group as the identity element.
So one thing, the factor group, the elements of this factor group should be within this set or it can be anything. Like you choose one Z, which is a combination of these three, right? Can I choose some arbitrary element B, which is a set of some other element which is outside this group?
They all will be within this because this is already a group. Because this is already a group, nothing will go outside this.
Okay. So means the
Factor group is just a collection. Collection of some elements, some people with some particular property.
Okay. Within this set, right?
Of course, within the set. Of course. Because once you are within the set, you cannot go out. Because then you will say, this is not a group theory lecture. Then okay. Say yes. Any question? So there is two remaining axioms, as I said, to prove. Inverse of Bim and Kate should be there. Bim and Burin and me are two groups. Bim and Kate are another group. When we multiply, we do nothing to them, from left or right. But somehow in real life, Burin is more powerful. If Burin multiplies, then. But I'm saying, so identity operator does nothing. That is proved here. Okay. So, Z, if you allow me, can I say it rho? Rho looks more like identity. So, I am saying Z because I have in my notes. So,
Just change the name.
Oh, changing the name. So, rho, now rho is rho. Do you agree? Rho is the set.
Just the closure property of this.
Yes. You'll get this. Okay? Okay. Then I need to show you. Yes. Okay, let me Okay, we have the invariant subgroup E, D and F. Take any element other than X. Oh sorry, other than EDF. What will you get? Do you expect to get EDF? No, definitely no, because X is not in this, and X is a group, subgroup. Subgroup has all the properties of a group. So when you do this, you will get some more. But that must be one of the elements from A, B, C, D, E, F. Okay? That way, now I would ask you A, B, C, D already I have, A, B, C, okay. Okay? So here you have E, D, F, E, D, F. Alright. This is what? Row. So I will have row A, row B, row C. How many elements I have? Here how many elements I have? 4. Here how many I had? 6. Here I have 4. Okay? Are they all distinct? Are they all distinct? No. At least row is different from row A. Okay? Row B, we don't know. We need to check it. Okay? Row C, we do not know.
So are you writing the factor group?
Yes, I am writing the factor group, but
Yeah, we have covered. We calculate from the process, the process.
I think you actually you have right before.
okay, let me first then write it, so then it will be more clear. So I have row here, which is E, D, F. I have row A, which is row A is A, AD, AF. Can someone tell me directly from there what is AD? AD. First D, then A. Huh? AD is B. AD is B. AF is C. Then row B is, here it will be B. C and A. Then row C is C. Huh? A and B or B and A?
A and B.
A and B. Okay. So how many? Probably you have row and row A as the distinct. Correct?
Two distinct, yes.
correct? Now let us find the inverse of rho A. Can you find the inverse of rho A? Is it rho A?
Two element group it should be rho A. Yes.
Inverse of rho A? I got an answer from Pradeep, it's rho A.
I think no. I think it's low.
That's two element if you want to make it group.
So rho A, okay? Since rho is identity, I can flip. I can bring A. Can I do this? And A is the inverse of A from the table. Right? So it's E. So, and rho is the inverse of rho because rho is identity. Okay. So rho A is the inverse of rho A because it's giving me rho. So that means this is your factor group. Identity exists, inverse exists, it is closed under group multiplication. So I take a pause here for any further question. Yes, please.
Sure for the low A, B, A, C, D, or because if D,
Hmm?
D, A should be C, right? For the low A, in shuffle, the
Rho A is
it should be A, C, D.
ACB. It doesn't matter, it's a set.
But it is
It doesn't matter, yeah. Maybe you were right, but it doesn't matter. All right. So, any question? So, it has been really nice interacting with you, and this is my first ever lecture as a teacher. So, really nice, wonderful experience talking with you, meeting new people. Thank you for giving me this opportunity, Burin, and thank you for always being here to encourage. Thank you, Pradeep, and all of us for your introduction. Thank you very much. Thank you. I must say, Khap kun khap. Khap kun khap.